Okay, Mary, you can go ahead.
Okay, thank you. So good morning, everyone. I'm Mary Barth. I'm from the National Center for Atmospheric Research, and I am chairing the session, Model Applications in Air Quality, Fire Weather, and Real-Time Prediction. And before we get started, I wanted to remind you all about muting your microphone so there's no extra noise when people are speaking. And then to ask questions, it seemed like the chat was working really well yesterday, but you are welcome to raise your hand as well and use the reactions tab. But we won't do questions until the end of the each talk. And if we didn't get to your question, we can get back to it at the end of the session. And then as a reminder, we are being live streamed on MCube YouTube channel, and this is being recorded. So let's get started. These are 15-minute talks. The first talk is by Toyoaki NAKARAI, and sorry if I messed up saying your name. And Toyoaki will talk about the consequence analysis of sulfur dioxide emissions from Shisakajima copper smelter. Please go ahead.
Thank you. I'm Toyoaki NAKARAI from Tokyo. It's just midnight. Okay. First of all, I would like to briefly introduce my presentation. At the end of the 19th century, due to SO2 emissions from copper smelter, conflict or pollution happened in many places because smelters are located in areas of densely populated, and also copper production increased by the introduction of new technology. So at Nihama, west side of Japan, copper smelters was relocated to an inhabited island called Shisakajima, nearly 20 kilometers away. However, in 1905, Shisakajima smelter began to operation. Adverse winds carried the smelter gas much more wide area. We used Dwarf meteorological data at Shisakajima to find out the reason why such an issue happened by wind load analysis and consequence analysis. Okay. This slide shows the location of Shisakajima. Okay, and Fig 1 shows we are working with Yokohama National University and red mark near Tokyo. And next slide. This slide is since the relocation was planned at more than 100 years ago, historical events were shown by this slide. Okay, events at Shisakajima smelter and relocation 1905, 1927, Hugo Petersen process, German process to produce H2SO4 to decrease the SO2 concentration. And finally, 1935, neutralization plant for dilute SO2 and the complete solution to pollution problem. Okay, and also 1971, new smelter was relocated again near Nihama, Toyo smelter. And the American people came here, and these smelters, Japanese 10 smelters, were model for US CAA in 1977. Okay, this slide is WRF data observed and observed data comparison. WRF data was in the location of Yokohama National University at Yokohama City. And the real data from Professor Fudeho, we changed the data to the windrows, and these tools in good relation. And in Shisakajima, WRF wind direction data and historical data, wind data should be compared to find out why these adverse wind in Shisakajima. This slide windrows each month, which shows strange phenomena from September to October, November. Only 3 months. ENE and E, while annual windrows shows EME and west, right to right, right to left, left to right. Okay. So we started to check the historical data, which was recorded more than 100 years ago. This is the 9 years average data. This is the historical data in 1927, but no solution for these data. And finally, we found this historical data in 1919. Here, time is 24 hours. The average on each month for 12 months. It's trying to say from September, October to November, WRF data, the same similar situation happens here, only three months. Okay, this is the 1915 and 1923. In between the formation of wind data, this is real data, original data, shows similar with the WRF data in 3 years, in 3 months. And the consequence analysis using FAST, which is from DNVGL, was performed. And there is a possibility in a situation, very slow wind and so on, down distance x-axis 20 kilometers and y-axis high concentration in ppm. Talking about the rice plant growth, there are 3 stages: rice planting in June and rice flowering in 80 days from rice planting, and rice harvesting in early October. So early September, sensitive to SO2 gas. We found, this is a conclusion. It was found that adverse winds carried out the SO2 smelter gas over the rice field at very sensitive seasons. It's September by windrows analysis based on WRF meteorological data. In 1939, neutralization process with ammonia solved complete solution to pollution problem. Why this process necessary is the adverse winds we analyze now. And then the smelter, new smelter in 1971, operated by flash furnace from Finland. This auto-pumped innovation in 1949 became a culture for copper smelter in the world after then. This is the evidence. Fig 18 shows, green line shows flash furnace increased in copper smelter because it's cost-effective, cost-cutting process, And also the SO2 in the furnace concentration is high, easy to make H2SO4. Thank you. Thank you very much.
So thank you, and thank you for staying up late to give your presentation. So far there are no questions in the chat, but I guess I'm wondering with the conversion, I assume the conversion of SO2 to sulfuric acid is done within the plant, and sulfuric acid is not being released to the atmosphere, but it's being mitigated as well. Is that correct?
I can't understand conversion problem.
Yeah, so you talked about the conversion of SO2 to sulfuric acid.
Carried by wind, and maybe it's reacted some kind of rain.
Right.
And in the paddy rice field, and it's an adverse effect, maybe, I don't know, but just I'm talking about the wind direction.
Right. Yeah, but certainly if sulfuric acid is being made and released into the atmosphere, then it does become, get incorporated into the clouds and be rained out as acidic rain.
But this time I'm only the wind direction. Adverse wind direction, and very strange phenomena was solved by Dwarf meteorological data. This data is very good.
was very impressive, and especially among a number of islands in the region that must be channeling the flow and using sea breezes. Yes. Okay.
Thank you.
Again, I do not see any questions in the chat, and so perhaps we can new questions could come up at the end of the session. So
my address.
Yes.
My address. Please send email to here if any question for Shisakajima problem.
All right. Thank you very much.
Thank you.
Okay, so let's go ahead and move on to the next talk. And so that will be presented by Ron Makatange. And again, Ron, apologize if I can't say your name properly. And Ron's going to talk about the experimental atmospheric forecasting system for Indochina and Southeast Asia. Ron, please go ahead.
All right, can you hear me?
Yes.
Yeah. Okay, you see my screen well?
It's perfect.
All right, so I'll talk about this experimental forecasting system that we're developing here in Chiang Mai, northern Thailand. So I'm Ronald Makatange, and I'm originally from the Philippines. And for this work, I would like to commend our research assistant and PhD student, Sharon Hassan Brand and Vanessa Surabipit. So we just made some website, but it's not yet fully public because it's still experimental. And currently we halted operations because we want to make some improvements, but we ran the model during the previous air pollution or biomass burning season here in northern Thailand. So my focus would be more on the Indochina part because we have the validation data for that. Let's move on. Okay. So this work or this system is based on the paper of our research assistant and PhD student, Sharon Hassan Brand. We just submitted this paper in Atmospheric Research Journal. It will come up soon, I hope so. Yeah. And so this is one of his major work, and we based especially the optimization configurations and initial validations on his work. For our domain, so this is our domain, so mostly in Indochina. So this system we operated last year, December 2021, which is the start of the cool dry season in northern Thailand, where we are. And we ran it continuously up to March, April this year, which is the peak biomass burning period in this region, and up to May this year. So May is like the monsoon onset in this region. However, this year, because of La Nina, the rains came a bit earlier and more intense. So that also somewhat affected how our forecast was doing. So for this talk, I will also focus more on Chiang Mai City in northern Thailand. So in this figure, the stars are the reference air pollution station over Thailand. So actually the other regions like Myanmar, Laos, Cambodia, Vietnam, mostly they have low-cost sensors. So we'll probably add them in the validation of this system in the future. So why did we just focus on northern Thailand? So during this period, according to the study that I showed earlier by Brand et al., so in the northern part of Thailand, so usually we get the brunt of these high PM 2.5 concentrations during the dry season in Thailand, reaching sometimes really high levels compared to other regions. Even in the central part where Bangkok is, it's during this period it's not really as high compared to the north. And so for this talk, I will also focus on only in the Chiang Mai city, because it's a big city, it's a tourist destination in a complex terrain, having a valley atmosphere, and because this is where we are, so we use the government's reference stations data, and in our institute we have a LiDAR, so we can validate the planetary boundary layer height as well. And this is the terrain of the Chiang Mai province, and Chiang Mai city would be somewhere here, a bit to the north of the province. So as you can see, the terrain profile, it's quite complex terrain with the highest mountain 2.4 kilometers. All right, so for this system, so this is our configuration. So we use version 4.1. So we use 9x9 kilometer horizontal resolution for Indochina. For Southeast Asia, which we just also experimentally run, but no validation yet. So we ran at 27x27 kilometers. So our HPC is still a bit limited, but hope we can upgrade that soon. So we used MODIS land use and CEP for meteorology boundary conditions. So we used the WACAM for chemistry boundary conditions. Anthropogenic emissions, EDGAR for the fire. We used the near real-time fire emissions. Biogenic Megan, and we used the go-kart aerosol scheme, again, due to limited our computational system. And we haven't yet tried with the data assimilation yet. So these are the rest of the parameters used for the meteorology, especially. So I'll show for this year's haze season or haze situation in Chiang Mai City from December 2021 to May 2022. So first I show, so this is a time series. So the red is the PM 2.5 concentration in micrograms per cubic meter. So the line is the forecast and the dots are the observations. Okay, and then the blue line is for the PBL height. So the solid blue line is the forecast, and the dotted blue line is the PBL estimate from the LiDAR that we have. So actually in December 2021, so see, we were, okay, I think the PBL height, we were getting, quite well, also for the PM 2.5, except for some instances there. And then as we go from December to January, so the biomass burning starts to begin, but still not yet in full swing. So still, I think we were getting, pretty good agreements with the observations for both PM 2.5 and the PBL height, except during the last parts of January, where you see the forecast was overestimating the PBL height, and that's probably causing this underestimate in the PM 2.5. So for February, so during the beginning, it's still okay, but during the last part where the biomass burning emissions start to increase, so yeah, the forecast was greatly underestimating at this point. And during the peak time in March to April, so we were really quite off. in the forecasts. It gets some of this, at least some variations well, but yeah, so most of the time we underestimate the PM 2.5. So during this time, it was because I think of La Nina too, so there were also some unusual rains that happened. So probably the model wasn't also getting the rains. But towards May, when the biomass burning stops, so it's go back to like in December and January and early part of February. So mostly also during March and May, the PBL height is also overestimated by the model, as you can see here. So some of the sources of error that we can think of is, so based on what Sharon did in his paper, which I will also show a bit. So probably some chemical components weren't captured. And maybe because of this, since we couldn't capture some of these chemical components, so that probably propagated to inaccurate aerosol radiation, PBL and cloud and up to rainfall, probably interactions. So in the next slides, I'll just show this chemical composition comparison that Sharon did over Chiang Mai City, but this was in 2019 because this was part of a campaign. And yeah, so we don't have this regular chemical composition measurements yet. So hopefully we can start with that. So from Sharon's work in 2019, during the peak time of the biomass burning. So these are like filter-based observations. So they use the filter to measure their PM 2.5. So this for the total PM 2.5. So see the model using two different aerosol schemes seems to do well, okay, for total PM 2.5. For the components, so for black carbon, I think the model was also doing quite well. And for organic carbon as well. However, when we go like to sulfates, so sulfate was greatly underestimated. And for nitrate as well, it's also underestimated. So probably this was also happening in this year in the forecast that I showed for 2022. But yeah, but we need like more like chemical composition measurements to really determine if it's coming from sulfates and nitrates. And probably because of that misrepresentation of sulfate and nitrate, so probably would affect the aerosol PBL interactions as well. So the next steps that we plan to use, plan to improve the system. So probably we'll use some local Thailand land use. So we use the MODIS one, which I think needs to be updated, and then use updated local anthropogenic emission inventory. So that's already underway. And also use some local biogenic emission data, since in the region, especially the one I showed in the northern Thailand, so a lot of forests. So that's also underway, and also to explore data assimilation. So also for the next step, so together with NCAR, we submitted some proposal to NASA Surveyor to, like, we start from this system that I showed you, and then together with the current system that's available here in Thailand, which mostly it's just like a visualization for the GEOS chemical weather data. And yeah, so we like to combine that and together with NCAR, yeah, to further improve our system, and together with the government data, reference sensor data, probably also low-cost sensors in the future, and together with some data assimilation capabilities. So basically, we just want to do something similar that was done for a similar system in India for Indochina as well. Thanks, that's all.
Thank you, Ron. Very nice. There is a question in the chat asking from Gordon Brooks, asking about whether you use the RRTMG radiation scheme or the RRTMG fast radiation scheme.
Okay. I think Sharon's here. Sharon, are you there? Maybe you can confirm that.
I'm going to guess it's RRTMG that most of us
yeah. Sorry, yeah, that's RRTMG.
Yeah.
Okay.
And then, so the next question is, do you know what year the latest MODIS land use data is from?
So the MODIS data, was it from 2010? I can't remember.
Yeah, I was going to ask, so, you know, did you maybe revise that as, did you download your own MODIS land use data, or did you use what was available from the WRF data websites?
Yeah, I think we used the one available from the WRF websites. And
So probably our WRF experts can say what year that's from, but I think it's a good point to try to have the most current, have yearly versions of the land use data available. So we have good representation of the vegetation in urban regions.
It's actually, there's a local land use data. I think we tried that. We tried to compare with the MODIS one. Yeah, I think we didn't see much difference, but yeah, maybe we have to try that out again. But that was the most updated.
And so Gordon has one more question, and then I'm going to go to Dave Stauffer after that. So Gordon asks which PBL scheme you used, and and if you used different ones.
So we used the YSU. So actually we tried other schemes, also MYNN, but seemed YSU was, I think, the one that captured at least the LiDAR observations best.
And YSU seems to struggle at nighttime and in the more stable regime, and that's what you showed that it.
I think for the nighttime, because our LiDAR cannot see below 100 meters. It's just a limitation of the LiDAR. So so we're planning to have like tethered balloons during night, so we can also get lower than 100 meters.
Nice.
Yeah, but that's still like a pilot program. So yeah.
Dave, could you please go ahead?
Yeah, that was my question too. And so YSU performed best? Is that what you said? Or you?
Yeah, well, we did some short, well, not really a full year or some full, only like a short time sensitivity. So we used, I think, YSU, I think also MYJ, I think, as well. And I think MYNN as well.
Did they all show the positive PBL height bias that you think is related to aerosol and radiation?
Yeah, I think so. Yeah.
And the MYNN, you used the EDMF version of MYNN?
I can't remember now. I have to look that up. Yeah.
Thank you.
And that's a good question, David, because there seems to be some changes in MYNN that would improve the chemistry predictions. So
yeah,
we're planning. I'm not sure the default's there yet.
Yeah.
But hopefully.
Yeah, we're planning to I'll use the more updated version as well. Maybe version 4.4 plan.
Okay, and there's a question for the WRF team, not for you, Ron, but so maybe that can be answered in the chat about whether there are plans to update the default land use data to a more recent year, or maybe another way to ask it is it possible to get land use data for specific years in case you're, if you're simulating 2012 or 2020, it's really useful to have those land use changes.
I'll comment on that. This probably we should talk to our land surface model people, and they are the ones that provide the updated land use data to us in the past. So maybe we should chat with them and see if we can do something about that. But the current MODIS data, I think, is in the early 21st century, 2003 through 2010-ish. Yeah, it is. But there are places you can get updated data, but quality control is one of the issues. And they have to process it, fill it with missing data, and so on. So the process, it's not simple, just download the data and use it as it is. So, but we can talk to the land surface model people to see if they have planned to do this.
Great. Thanks, Wei. Okay, so there are no more questions. So let's go ahead and move on to the next talk. And that talk will be given by Giorgio from the Cyprus Institute. And George will be talking about the evaluation of Dwarf Chem model, real-time air quality forecasts over the Eastern Mediterranean. So George, we can see your slides and full screen, and we can hear you.
Okay, can you hear me? Okay, thank you very much. I am Giorgio. I'm a postdoctoral researcher at the Cyprus Institute, and I'm going to describe our forecast setup using the WRF Chem model. We are performing daily 3-day air quality forecast over the Mediterranean and Cyprus. We are using the RAGM chemistry mechanics with Mesoscale with VPS for aerosols, and that's came out 108. As you can see on the right, you are using 3 one-way nested domains. The first domain includes, it runs at 50 kilometers and includes the major dust sources in the region, which are the Saharan Desert and the Middle East deserts. You know, dust is a very important factor of air quality in our region. The second domain runs over the Eastern Mediterranean in 10 kilometers, and the third domain focuses over Cyprus with a resolution of 2 kilometers. For the boundary conditions, we are using the GFS model for meteorology and the WSECM model for chemistry. For emissions, we are using the EDGAR HTAP version 2 for anthropogenic emissions, the MEGAN model for biogenic emissions, while for dust and sea salt, we are using GOCART. For the island of Cyprus, we have incorporated a high-resolution anthropogenic emission inventory from the official authorities of Cyprus. We actually got an emission inventory in a horizontal resolution of 1 by 1 kilometer, and we upscaled it to 2 kilometers, which is our in and post domain. We can see on the top right how the new emission inventory compares to the EDGAR emission inventory in terms of the horizontal resolution. Of course, we can see that anthropogenic activity is much more discrete in the new emission inventory, but there are also differences in the emission totals, especially for CO and NOx. We can see in red color that we have much higher emissions from the new emission inventory. Apart from this, we also applied monthly, daily, and hourly emission factors according to lot of euros for documentation, and these factors are calculated per species based on the primary emission activity in Cyprus. And we can see here, for example, the hourly emission factors for CO for summer in red color and for winter in blue color. The incorporation of this emission inventory resulted in an important improvement in the model performance. We can see here the blocks plot. We can see the observed values of NOx in gray color, in blue color with the simulation with the EDGAR emission inventory, and in red color with the simulation with the new emission inventory. And there is actually the major differences are observed at the urban sites, which was expected. And there is actually up to 60% improvement in the estimation of the concentrations of the atmospheric pollutants at the urban areas. And as we can see, here is the diurnal profile of the NOx concentrations, and there is more accurate representation of the diurnal profile of the atmospheric pollutants. We are using this setup to perform, as I said before, 3-day air quality forecast. So in order to evaluate this, the forecastability of the model, we used the 3 winter and the 3 summer months of 2020, and we compared the data from the model output, the forecast output, to data from 9 ground stations over Cyprus, and we also compared the forecast performance to the performance of CAMS. So here we can see the NO2 on the top and ozone concentrations on the bottom for winter on the left and summer on the right. Of course, there are higher NO2 mixing ratios during winter due to higher emissions during winter and due to less intense photochemical activity. Near the urban centers, of course, we have higher concentration due to anthropogenic emissions, and these high concentrations at the urban centers result in reduced ozone concentrations at these locations. And we can also see that in the summer, there are high concentrations all over the island. This is an issue in our region. We have high background concentrations. And during the summer, there are also exceedances in the ozone concentrations, exceedances of the limits set by the European Union. Here we see how this compares to observations and the CAMS forecast. With gray color, we can see the observations, with blue color, the WRF model, and with red color, CAMS. We can see that there is an important improvement compared to CAMS, especially at the residential and the traffic stations. But we can also see that there is an overestimation at the industrial stations, and this is something we are looking at. We believe this is due to the emissions height, because in the model, the emissions are actually emitted on the surface, while at these stations, due to the chimneys, the height of the chimneys, pollutants are emitted on a height of about 70 meters. And this is something that we will incorporate in our future simulations. And we can also see there is also a small improvement in the prediction of ozone concentrations at the residential and traffic stations. This is then diurnal profiles of NO2 and ozone at all the stations under investigations. And as expected, we have more accurate representation of the diurnal profile of NO2 at the residential and traffic stations. Of course, at some stations, there is still underestimation, but this is due to the fact that these stations are located very close to main roads. So it's actually impossible to capture every car passing by and the emissions from the exhaust. And in alignment with NO2, we consider there is also improvement in the representation of the diurnal profile of ozone. These are the results for winter. Similar results were shown for summer as well. These are the exceedances of the daily maximum 8-hour average. And actually, during the summer, because during the winter, we didn't have any exceedances, we saw that at the background stations, we had 35 exceedances according to the measurements. 22 exceedances have been successfully predicted by the WRF model, while CAMS show predicted no exceedances during this period. At the residential stations, we had 20 exceedances, and seven of them were successfully predicted by WRF, but only 2 by CAMS. Of course, we also had some false alarms by the WRF model, and this is due to the overestimation, the slight overestimation we had in ozone concentration during the summer. These are the results for PM2.5 for winter on the left and summer on the right. We saw that there is a similar behavior by WRF Chem and CAMS. Actually, both models had equivalent performance, and we saw that there was a small overestimation of background PM2.5 concentration during winter. We further investigated that, and we saw that this was due to increased model concentrations for a period from two-day period from 12 to 14 of December. And these are the subcomponents of the PM2.5 during those days. of course, we have increased sulfate aerosol concentrations, which is in agreement with previous studies. But during the period under investigation, we saw that we had increased primary PM2.5 aerosols. This variable in the mother aerosol mechanism also includes fine dust particles. Actually, 3% of the directly emitted dust goes into primary PM2.5. So we end up to the conclusion that this overestimation is due to dust, which is something that we will work on in the coming weeks, because as I said earlier, dust is a major component of air pollution in our region. So to conclude, we have employed the WRF Chem model to produce accurate air quality forecast over the Eastern Mediterranean and Cyprus. By improving the spatial and temporal resolution of the emissions, we saw an improvement of the scale in the representation of the magnitude and the diurnal profiles of atmospheric pollutants, especially near the urban centers where the majority of the population lives. We had, as I said, an important improvement in the magnitude of the forecast of NO2 and ozone. WRF Chem was able to predict ozone exceedances with higher accuracy compared to CAMS. Both models had similar performance in terms of forecasting PM2.5 concentrations, and we end up with a take-home message that is that regional coupled online air quality models can provide real-time air quality forecast, improve the real-time air quality forecast, and at least for short-lived species that undergo photochemical reactions compared to the state-of-the-art global chemical transport models. What I have showed, you can find it actually in two publications. The first one was published 2 years ago and deals with the implementation of the anthropogenic emission inventory. And the second one was published 10 days ago, and it deals with the evaluation of the forecasting system. So thank you very much for your attention.
And thank you, very nice talk. And it's always great to see WRF improve the air quality forecast. Because CAMS is a very well-known good air quality forecast, global forecasting system. So that's definitely nice to see. There are no questions in the chat yet, but maybe one quick one is that you focused a lot on, say, the NOx control of ozone. Are there times when there are VOC controls of the ozone? Because you didn't really show, how the VOC volatile organic compounds were performing compared to observations.
Yeah, actually, we haven't got into too much into the VOCs, but it seems that the major component controlling are the NOx.
Okay. And with the dust, you use the go-kart scheme. Are you planning to try different?
Actually, this is something we are starting to work on, and at the first step is to also evaluate the performance of the AFWA schemes. And there are also some papers out with modified dust factors for go-kart, and we also want to try all of these to see which one performs better, and probably end up to a better forecast for dust, because this is a really important issue in our region.
Yeah, definitely. Yeah. Great. So a question just came in from Gordon Brooks. Do you use any particular model for dust transport forecasting is the question. So I'm not if you feel like you can answer that, please go ahead.
Actually, we're not using any other model apart from WRF Chem. The go-kart dust schemes runs through the simulation online with the WRF Chem. So the go-kart scheme actually provides the dust emissions in the WRF Chem model. I hope I answered the question. Yeah,
I think there are factors that come in in terms of, again, the data sets, soil erodibility, the soil moisture, et cetera, but also things like the type of clay matters or can matter. And so there's definitely a lot of improvements that can be done in our dust work. Okay. So there are not any other questions. So let's move on to the next talk. Thank you so much.
Thank you.
That was
Thank
very
you very
good.
much.
Yeah. And our next talk is being presented by Miguel Carmona. Miguel will be talking about modeling transport of Saharan mineral dust of the Iberian Peninsula, a multi-scheme assessment of size distribution and optical properties. So we can now learn even more about how well we are simulating dust in WRF Chem. Miguel, are you able to present
yes.
your...
Hi everyone. I'm going to share my screen and let's start. Okay, I hope everything is good.
Looks good.
Okay, so good morning or afternoon in my case here in Spain. I'm Miguel Pino from the University of Granada, and I'm going to present some preliminary results of the work I'm currently immersed in about the comparisons of different aerosol schemes in WRF Chem with Guadalupe Sanchez and Jose Antonio Ruiz. So thank you for coming and let's start. And let's start first with some study context. The objective of our work is the evaluation of three of the most usual aerosol schemes in WRF Chem: GOCAR, Mosaic, and MAPE, under a dust outbreak in the south of the Iberian Peninsula occurred between the 22nd and 25th July of 2021. To do so, we will first make a calibration of the total amount of dust predicted, and after that, we will make a comparison between the aerosol optical depth predicted and the aerosol optical depth measured. The reference data will be the Aeronet inversion data for the calibration and the Aeronet aerosol optical depth measures, also from Aeronet, for the optical comparisons. So in this figure, we can see some qualitative evolution of the outbreak. As we see, its source is in the Saharan Desert, and it comes to the south of Spain, where we have highlighted the province of Granada. Precisely in this province of Granada, we have two Aeronet stations: the Granada stations, that is in the city, and the Cerro Pollo and the Cerro Pollos stations, that is in the mountain. There is a difference of more than 1 kilometer in the elevation between the two stations. Now in this figure, we have an example of the Aeronet size distribution data that we have available in the Aeronet inversion data. As we see, we have a set of volume concentrations for several radii. If we interpolate these volume concentrations, we achieve a volume concentration function that can be integrated with respect to the natural logarithm of the radius to obtain the total volume concentration. Some kind of measure of the total amount of dust present. Okay, so having said a few words about the Aeronet data, we'll make some comments about the aerosol schemes. First, we have that GOCAR, Mosaic, and MAPE have all the same dust emission scheme, the GOCAR dust emission scheme. Dust emission flux in this scheme is governed by equation 1. As we see in equation 1, we have written in red the C parameter, also known as CH dash in WRF, whose role is to fit the total flux, and that will have a very big importance in our calibration. However, even though we have the same dust emission scheme for the three aerosol schemes, we have that each one has a different dust size distribution, as we can see in this representative figure. As we will see in a few frames, the GOCAR distribution fits better to our results. So having said this, the approach we will take to the calibration will be performing 4 simulations with GOCAR using multiple values for the CH dust. After that, we will compare the total dust volume concentration predictions with the aeronet volume concentrations data. With that, we will find an optimal CH dust, minimizing the mean square differences between the GOCAR predictions and aeronet. Now in this figure, we can see the 4 simulations performed, both for Granada and for Cerro Pollos, with the multiple CH dust values. And using the method we commented before, we obtain an optimal CH dust value of 0.655 square seconds over square meters. On the other hand, the recommended CH dust value in Dwarf for the Saharan Desert is 0.65 square seconds over square meters. So our optimal CH dust value is less than a 1% different than the recommended value by Dwarf. So hereinafter, for all the simulations, we will use the CH dust value of 0.65. Now in the figure below, we can see the comparison between the different aerosol schemes using the CH dust 0.65, both for Granada and for Cerro Pollos. As we see with the same CH dust, the made aerosol scheme is the one that predicts more volume concentration, and it's followed by Mosaic. However, the 3 aerosol schemes have a very similar time evolution. And now, as a little summary of the calibration, we have that the optimal CH dust obtained is consistent with the value recommended in Dwarf, that the dust concentration predictions are bigger for made followed by Mosaic, even though the 3 have a similar time evolution, and that even though the 3 emission schemes share the dust emission, they differ in the dust size distributions. So our hypothesis is that the dust size distributions among models have an impact in the total dust volume concentrations. This finishes the calibration part, and now we move on to the aerosol optical depth part. In this case, the approach will be the performance of 3 simulations, one for each aerosol scheme, using the CH dust of 0.65 and the volume approximation optical scheme, the first scheme in Dwarf. With that, we will compare the aerosol optical depth predictions by Dwarf with the aerosol optical depth data from aeronet. And we will also study the dependence of the wavelength for the aerosol optical depth. In this figure, we can see the aerosol optical depth time evolution for 4 different wavelengths at Granada. Now, we can see that even though GOCAR was the aerosol scheme that predicted less volume concentration of dust, it is the aerosol scheme that predicts more aerosol optical depth in the 4 cases. On the other hand, for upper wavelength, may predict more volume concentration, but it predicts very small aerosol optical depth, even to the point that at 1020 nanometers, it's very close to zero. We can see that at Cerro Pollos, we have a very similar behavior. So now, to better understand the aerosol optical depth wavelength dependence, we will use the equation of the lower left corner, and we will study the parameters beta and alpha. Alpha is known as the angstrom exponent, and it gives a measure of the size of the particle. So if we have low values for the angstrom exponent, we have big particles, and if we have big values for the angstrom exponent, we have small particles. With this in mind, we can see that MAVE sees small particles. Small particles more proper than from urban aerosols than from dust. On the other hand, if we see mosaic sees very big particles of a size quite bigger than the observed one. GOCAR is the one aerosol scheme that predicts an adequate angstrom exponent. Now, regarding to beta, that can be interpreted as the aerosol optical depth at 1 micrometer, we see that both GOCAR and mosaic have an adequate behavior, while the behavior of MAVE is very bad. At Cerro Pollos, we can see a very similar behavior. So now, to summarize, we have seen that under the same CH dash, the optimal one for GOCAR, we have that MAVE was the aerosol scheme that predicted the bigger volume concentration of dust, but the least aerosol optical depth, while GOCAR that predicted less volume concentration of dust predicts more aerosol optical depth. With respect to the agreement with beta and alpha, GOCAR and mosaic have a good agreement with beta, that is, with the aerosol optical depth at 1 micrometer. On the other hand, GOCAR is the unique aerosol scheme that has a good agreement with the angstrom exponent. With this, and recalling again that the three aerosol schemes have the same optical module except for a redistribution function of the sizes, we have the hypothesis that mosaic could improve with a better redistribution of the dust sizes. However, work must be done in order to confirm that. So thank you everyone again for coming, and that's all.
Great. Thank you so much, Miguel. That's very interesting. So thus far, there are no questions in the chat, but to follow up on your last comment about the optical module, if I recall, you can choose whether your aerosol particles are well mixed or a core shell configuration. Which did you choose? And I assume you use that same setting for all the different options.
We saw a little bit all the 5 options available in Dwarf, but the first one, the volume approximation, seemed to be appropriate and simple enough for our purposes. So we choose it. But probably there would be a good idea to prove also with, for example, the shell core approximation.
Yeah, I'm not sure there's really observations to guide you on what the aerosols are. So it's just good to be consistent, I guess. I don't see any other questions specific to your talk. So thinking that the dust is coming from the Sahara, I'm wondering if that the go-kart estimate of the C value is good because of that. And I guess, some people have looked at other deserts and that C value is not as appropriate for other deserts, but it was really good to see confirmation that your estimate matched what go-kart or the Dwarf go-kart scheme suggested.
It's very good. It's less than a 1%.
Yes, yeah, very nice. Okay, so I think there's a question in the chat that's not related to any of the talks, and maybe I'll just answer that really quickly. It's about asking whether WRF Chem can be configured for a remote city like Manaus in the Amazon, and what input data you need. Really, the answer is yes. And I think maybe the best thing to do, I know that Manish Srivastava has done a paper looking at aerosols in that region, Go Amazon studies. So I would suggest doing a literature check and see how they configured their models. Okay, so in the meantime, let's move on to our next talk. And our next talk will be given by Prashant Singh from Goethe University in Frankfurt. Prashant will be talking about vertical distribution of aerosols during deep convective event in the Himalaya using Dwarf Chem model at convection permitting scale. Prashant, are you able to share your screen? Okay, we can see your screen now, and if you can go to present.
Okay, so
Perfect.
I'm going to present on the vertical distribution of aerosols during deep convection event over Himalaya. So this work was performed with EC mode in Nepal. So I did simulation of WRF Chem and WRF at convection resolving scale and one bigger resolution like 25 kilometer and the 4 kilometer for the Kedarnath flood case. Kedarnath flood was in 2013, where lots of people have lost their life, infrastructure loss and other stuff. So many studies was there which explain the westerly and the impact of westerlies and monsoon, forwarding monsoon over the Kedarnath flood. But I wanted to check what happens when with the aerosol and this stuff during this event. So we work with the WRF at different scale. And last year we published this result in atmosphere. So you can see from the WRF Moscard simulation at 25 kilometer and 4 kilometer resolution. So you can see from topography, Kedarnath is just near to the western border of Nepal and southern tip of the Himalaya. So when we compared with the Moscard WRF at 25 kilometer and WRF without aerosols, you can see the precipitation was quite good captured in the model. But when we see the Moscard minus WRF Moscard minus WRF without aerosol, you can see there is a about 40 plus millimeter difference over this region near to Kedarnath. And when we see over the convection resolving scale, similar result you can find out for convection resolving scale. Also, there is a difference of 30 to 40 millimeter over that region. So we tried to compare with the nearby observation stations. So there we found like 4 to 5 stations near to Kedarnath place. So you can see observations was in blue, and TRMM near over those points was in green. And all the simulation with chemistry, WRF with chemistry, WRF without aerosols at 25 kilometer, and at convection resolving scale performed quite well over those reasons, but there is a slightly time lag, like prediction was quite 2 to 3 hour lag was there with model simulation. And on 16th and 17th June, if you see, there is a like cloud cover was also captured quite good in the model over those reasons. So we wanted to see like what's vertical structure of the aerosol. So you can see there was a strong low pressure zone over the eastern India, which propagate on 16 June over the central India, and lots of humidity was vapor was coming toward the Himalayan region, which pressure level, low pressure zone moves over to Kedarnath or Western Nepal area. And 17th June was the day when the flash flood comes over Kedarnath, and that system moves over the Western Nepal on 18th of June, and then on Western Nepal, we had again flood in Western Nepal, and then 19 June and 20 June system got disappeared. So you can see near surface black carbon. So these are the IGP region where the high concentration of black carbon was present. But when we see over 500 HPA and 300 HPA, you can see there is a trapped black carbon, or we perform similar analysis with the sulfate and other stuff too. So you can see on 15th, 14th and 15th, there is at 500 HPA, significant amount of black carbon and other aerosol was trapped in, which moved on central part and the western on 17th over near to Kedarnath. And similar you can see over the 300 HPA. So there is a vertical updraft of the black carbon and other stuff was observed. Then we tried to calculate the vertical column concentration, and you can see on 16, 17 there is a strong change in the upper level over these regions. So on 16 and 17 over Kedarnath, and also there is a change in the ice number and rain concentration over the Kedarnath region with presence of aerosol at both 4 and 25 kilometer. So this was yesterday with Kedarnath, but when we had performed 1 year long simulation with WRF came, and we found out during pre-monsoon and monsoon season, there is like a significant black carbon is simulated in the WRF chem at 500 HPA and above, which we tried to collaborate with, try to see with the Calypso data. So Calypso smoke data, you can see there is a significant number of absorbing material is present. So at pre-monsoon season, there is black carbon and other stuff over 500 HPA and above is mid-troposphere, where most of the cloud forms in this region. So you can see during the deep convection from the IGP region, there is a strong updraft of the black carbon toward the Himalayan region, and all is very significant. So this was, and further it impacted the verticity and other stuff too, which add on the effect of Kedarnath flood. So this is all from my side, which says like with presence of aerosol, it's like 40 to 100 millimeter changes was observed in model, and then with other CAPE and other values also significantly changes was over those reasons. So thank you.
Thank you, Prashant. Very nice. Let's see. Yeah, I don't see any questions in the chat yet. Maybe just to clarify your WRF Chem model configuration, I saw that you use Mozart for your chemistry option. Is that correct?
Yeah.
Okay, so that's the Mozart gas chemistry with the go-kart aerosols. And with that, you're able to allow aerosol radiation feedback. And did you have that activated in your model simulations?
Yeah.
Yeah. And I'm just trying to think through. So, and you can't actually do the aerosol cloud interaction analysis with go-kart because it's a bulk scheme and not a, it doesn't include the size distribution. Yeah, I guess I'm trying to understand, is there a radiative impact that you think is affecting the precipitation?
Actually, in this study, we were trying to see the vertical updraft of aerosol and the concentration of aerosols with deep convection. So mostly I think with presence of aerosol feedback, it's like change of cape, and verticity is mostly due to radiation changes in that region. And if you see in precipitation, where we have a low level cloud, there was a like negative impact of like less precipitation. So mostly due to radiation feedback only.
Right. Okay. Thank you. A question just came in on the chat from Daewon Kang, asking which convective scheme that you use, and I assume for your 25-kilometer grid spacing.
I think I use Kane-Fritz scheme.
And so Kane-Fritz in the meteorology, and then you had convective transport turned on in the chemistry, which I think is the G3. Yeah, but it uses the Grell, one of the Grell convective schemes. So there's a slight difference between meteorology and chemistry in the convective schemes. Yeah. So I'm just kind of thinking through any other questions for Prashant. I don't see anything more in the chat.
Thank you.
Yeah, thank you. It's very interesting. It's one of those things where I wish we were in person and we could talk more offline.
Yeah, thank you.
So thanks a lot.
Thank you.
So yes, let's go ahead and move on to our last talk of the session. And that talk will be given by Maria Fidiani, and who's from NCAR, from the Research Applications Lab. And Maria will be talking about the firebrand parameterization in Dwarf fire, simulations for the Marshall fire. Maria, are you here?
Yes, can you hear me?
I can hear you. Oh, there you are. Hello.
Hi, I'm gonna share my screen. All right, can you see it in presentation mode?
It's in the presenter mode. So are you able to get to the top and swap screens?
Swap? Does
Perfect.
that?
Yeah, that's great. Thank you.
All right, awesome. Let me find my cursor here because now I'm a little lost. All right. So the development of the firebrand spotting parameterization started as an effort supported by the Colorado State. It was part of the COFAP's Colorado Fire Prediction System project. The original code has since evolved into a module that is now part of the WRF ARW community code base. I think that this development was significant because firebrand spotting is a major contributor to spreading of wildfires. And firebrand transport parameterization is finally part of WRF, meaning that it's accessible to researchers and students, offering a unique potential to crowdsource research and development from national and international organizations, leading to substantial advancements in the field. So firebrands are burning pieces of vegetation, also known as embers, that are generated at the fire source and carried with the wind into unburned areas, potentially igniting new spot fires. Short distance spotting accelerates the fire rate of spread by expanding the fire perimeter slightly beyond the fire front, whereas long range spotting can ignite new fires several kilometers downwind, possibly in areas beyond containment boundaries. In the figures, the figure to the left, you see an infrared image captured by the Colorado multi-mission aircraft showing a spot fire during the early stages of the Cameron Peak fire, in which firebrands were carried over a highway and a creek. In an urban setting, so in an urban setting, embers are the leading cause of home ignitions during fires. That's because they accumulate in gutters and vents and may be able to reach more flammable structures within the houses. Embers play a significant role in spreading wildfires and are of critical importance in the wildland-urban interface. Why is my, okay, got it. The firebrand's parameterization is composed by three major parts. The generation part, I don't know if you can see my cursor. Let's assume you do. The generation part is of the code is what decides the locations in which the will be the source of the firebrands. Transport in physics is the part that calculates the processes experienced by each individual firebrand particle, and lending calculates what happens to particles that do not burn out and descend below a specified height threshold. In the generation process, firebrands are cyclically generated from sources along the fire front, where the fire rate of spread and fuel load are high. Once the source grid points are selected, these particles are distributed over multiple vertical levels, and then the firebrands are transported with the resolved atmospheric flow, and they burn out as they are advected and settle. The firebrands may burn out while in the air, or they may land if their trajectories descend below a specified height threshold. Particles that land before complete burnout are then accumulated in a two-dimensional field. The field obtained from the spatial accumulation is used to calculate a likelihood of new fire ignitions due to spotting. The spotting likelihood is basically the spatial fraction of landed firebrands within the interval between consecutive model outputs, scaled by the fuel mass on the landing location. The Marshall Fire is arguably the ideal case to illustrate the importance of modeling embers in a fire simulation. The Marshall Fire was the most destructive in the state history, destroying over 1,000 homes. The fire started as a grass fire in the outskirts of Boulder and reached the residential area in about 1 hour. The fast rate of spread was driven by extreme high winds from a downslope windstorm. The combined high wind speed with relative humidity and flammable vegetation resulted in high fire intensity, rapid fire growth, and showers of burning embers starting new fires. It has been observed that when wildfires reach the urban areas, the pattern of home destruction accompanies unconsumed shrubs and trees, indicating that most ignitions are likely due to burning embers accumulating in flammable structures on or around the houses. In the simulations of the Marshall Fire that I'm showing today, they were created using a mesoscale to LES configuration, meaning that the outer domain had a 1 kilometer grid spacing and used PBL parameterization, and the inner domain was about 100 meters grid spacing and used LES. So in these animations, what you see is the fire area indicated by the black line, and the percentage of firebrands landing ahead of the fire front indicated by the colored scale. On the left is a control simulation, and on the right is a simulation showing the fire spreading with additional 5 spotting locations in addition to the primary ignition point. So even though automatic spot ignitions are not part of the parameterization, the fire locations and times were chosen based on the output of the control run. Okay. So what you saw in that control animation was the fire being contained by Marshall Road and Highway 36. The fire is really unable to spread across these barriers because in the model's fire fuel layer, roads have no fuel, which is a realistic representation, but with a consequence of creating a barrier. So if you pay attention, when the fire spreads southward, it doesn't really spread over Marshall Road. It spreads around Marshall Road. It never spreads over Marshall Road. And that's because of those containment barriers present in the fuel layer that we use in the model. So when we remove the no fuel points by setting a uniform fuel layer, we notice that the granularity of the different fuels is actually essential to reproduce a realistic rate of spread. On the left, you have a simulation with uniform fuel, assuming grass only, while on the right, you have the traditional fuels that we've been using in the model with the additional spotting ignitions. So, of course, this is not to say that the current fuel layer is accurate. It is not, because urban fuel points are actually contain no fuel. So, but what we see here is that the fire behavior is quite sensitive to fuels, and we do need the representation of those containment boundaries, and we also need spot fires to ignite across these barriers. So it's worth noting that typical wildland fires are different than the Marshall Fire. Nevertheless, when we're in high wind conditions, firebrands still contribute to an increased rate of spread and spotting across barriers. So there's another example here, and this is from the Cameron Peak Fire, where a spot fire ignited across the highway and the creek. You'll see the infrared image showing spotting with a distance of at least 450 meters. And in this case, one source of uncertainty in large fires, such as the Cameron Peak, is the perimeter timestamp. Because the fire duration is multiple days, the simulations must be initialized from a fire perimeter. These perimeters are created from satellite imagery, and they often include additional aerial methods. So it turns out that the information there in those perimeters actually pertain to a temporal window. And so uncertainty in these perimeters timestamps are inherent. In this animation, you see a set of simulations with varying ignition times used to represent the uncertainty in the perimeter ignition time. I considered those 4 members an ensemble, and you see that they show multiple clusters with high fire spotting likelihood. All of the ensemble members indicate high likelihood of spot fires in the region across those containment barriers. On the top right, you see the firebrand accumulation over a 24-hour period, and that illustration shows the potential hotspots prone to fire spotting. You see 3 main regions here across those barriers. And there were extensive firefighting operation to suppress the fire and to protect campgrounds that were around Chambers Lake. And they were successful for a short period, but we all know that fire became the largest wildfire in Colorado history. And then in the illustration below, you see the spotting likelihood showing hotspots when we take into account the surface fuel in the locations where firebrands land. So these fires illustrate the importance of modeling embers in fire simulations because it reveals, because they reveal critical model limitations, which is the lack of spot fire ignitions. It is really not feasible to run ensembles for urban fires and wildfires that may advance into the urban zones because the fire does not spread. It remains contained with those no fuel barriers. It also limits research advancement. For example, in the case of the Marshall Fire, this is a strong case to investigate model errors and sources of uncertainty because there was no active suppression from firefighters. And suppression is something that we cannot yet include in the model. And so the Marshall Fire is a small area case. It's a short case. And so it would be a really great opportunity to have that a case study to really explore uncertainties in the coupled model framework. It also hinders efforts to develop urban fuels representing those residential areas in that the research that could be done using coupled simulations or ensembles would still encounter the no fuel obstacle. And ultimately, a significant component is missing, right? Burning embers are blown by the wind. They ignite spot fires near and far ahead when they land on flammable surface structures and surface, rather on an urban setting or in a wildland. And so to finalize some of the challenges associated with this research and other wildfire research using the coupled framework is that there are a lot of unknowns. For example, emission properties for those fire brands like size, mass, and temperature. We don't have a good sample of that. Burnout physics is really, we're assuming spherical particles. And for model verification, challenges include a ton of uncertainties, most of them associated with the atmospheric components that we already know and fire behavior processes, and the data scarcity and inconsistencies across fire spotting observations and the frequency and resolution of perimeters with their corresponding timestamps. That's all I've got. Thank you.
Thank you. That was very nice. We had a couple of a comment in the chat that also got answered, but maybe you can expand on it. The question is it possible to use Dwarf fire with Dwarf Chem? What resolution is optimum to capture fires?
I don't think that fire is coupled with Chem, but the possibility for developing is there. As far as I know, people usually run a fire simulation, a coupled fire atmosphere, and then use the output to run Dwarf Chem with that information, but I'm not sure about the details.
And I should have gone on because Jan Mandel said, yes, Dwarf S-Fire does that, and that there's a talk after the break on Dwarf S-Fire. But do you have a comment about what resolution is optimum to capture fires?
So we are running in LES mode. We want for the fire run in a refined grid. So whatever is the resolution of your inner domain, you can refine that even further for the fire behavior model. So in this case, I'm refining it 4 times. You can set this to a different number. But you want it to be in LES mode. You want the model to be able to represent the microscale processes.
And I imagine it's important to have high vertical
Yeah,
distribution, right?
yeah, in addition, yeah.
Okay. And so there's a question from Adam Kochansky. How does the model account for the distribution of sizes and shapes of embers and the fact that spherical and non-spherical particles are advected differently? What is the range of sizes and the embers in the model?
That is a great question with a very simple answer. Right now, we're assuming spherical particles only. As far as I know, there's very little research that gives us data to include that information in the model. That this is like the version 0 of the parameterization. And so we just started with what we know, and we just want to see the embers being transported and how much potential we have to advance the model from there. Yeah, but if Adam has more information and is interested in, sharing ideas, is very welcome.
So yeah, maybe I didn't quite catch it. So when you have embers released, are they all one size?
They start with the same size, the same properties, same temperature, same density, same everything. There is the possibility of enhancing that feature in the model. But right now, this is what we've got. We just got a uniform distribution, and what is configured is pretty much the number of embers that are released and the frequency in which they are released.
Yeah, lots more to do.
Yeah.
Jimmy Didia made a comment that says, note that Marshall Fire spread with high winds and suppression was not possible for the first few hours. And so I'm sure that was a factor too, especially as the fire traveled from, not really populated area into the Louisville and Superior region. Yeah. One more question, and then I think after that we can take a break. Is there any additional computational cost with fire spotting enabled?
For sure. I haven't tested it after incorporating with the official WRF release, but the test we've done with the version of the model that went for the Colorado State, that was about 15%.
Okay. Coming from the chemistry side, that's not too bad. All right, that was a great talk. All the talks were very good. I enjoyed them all. And I think we're taking a break. I don't know, Wei or Kelly, if we have any announcements. And if not, go ahead.
Thanks, Mary. Yeah, thanks everybody for staying on time. It's perfect. We'll come back in about at 10:45. But for those who want, the speakers who want to try to share their screen during this break time, you can stay on. We'll work with you to see if you can bring up your screens. But otherwise, we'll see you in a few minutes. Thank you. Thanks, Mary.
Hi, Wei. This is David Evans. Can I try sharing my screen?
Yes, please.
Okay. So yeah, I'm curious if it goes to sharing the Zoom or if it shares. All right, you see my slides,
yes,
not Zoom.
It comes up very nicely and a full screen too. Yeah,
great.
You can advance the slide. Yeah, then you're good. You're good.
Okay.
Go. Yes.
Great.
So David, you're giving the talk and not Cliff. Is that right?
That's right. Cliff is out of the country.
Okay, I will make note of that. Perfect. Thank you.
Yeah.
Sorry, Bill, I did not.
Yep, no problem.
Tell you that. Yeah. So is he vacationing?
No, well, no, he's given a talk in Israel. So yeah, he's halfway across the world right now.
Oh, okay. Well, it's good to have you around.
Yeah.
All right. Anybody else from the next session?
Hi, Wei. This is Adam. Yeah, let me try that because
Very
I
good.
think I'm first in the next session. Yes.
Oh, yes, yes.
All right, so let's try.
And welcome to the workshop, Adam. Yeah.
Okay. Is that full screen?
Yeah, looks good. And
All right, okay,
you can
cool.
move your slides a little bit. Just advance it. Yeah, I think you're
good.
You're good. You're good to go. Yeah, yeah. Okay. All right, let me see. I think all the, I was checking the speakers. I think they, I don't know if Brad has joined. Ula, are you there? Oli, I guess I said it wrong. Oli, are you there? You want to try bring up your slide? Oh.
Yes, see.
Okay, just to give it a try.
The preview, let's see, first slide is share screen. Just one. Okay, allow Zoom to. Zoom.
Yeah. Okay. Yeah, it's coming back. And
You
you
can do
have a
like,
way to advance the pages. Okay. Okay. All right. You're good.
good. Escape and stop sharing.
Okay. Okay.
So the same-
And George Humberto, if you're on and you want to try, bring your slides up.
I think it's Jorge.
Oh, yes, I'm here. I'm here.
Okay. Do you want to try to bring up your slides? Okay.
Yeah.
Okay.
Of course. And right now.
It's coming up. Okay. I think we're good to go. Yeah. All right. Thank you. Yeah.
So is it Jorge or George?
Sorry.
I really like any name like Jorge or George. I also call me Humberto, my second name. All is fine for me.
It looks like your voice is broken up a little bit. Yeah, if you maybe when you're presenting, you can turn off your video.
Okay, my voice is not good. I need. Okay, more clear, more strong.
Your voice is fine. It cut out for a second, so it seems like the internet was a little bit unstable or there was too much bandwidth. So she was just suggesting that if you turn off your video like you just did, then that might save some of the bandwidth. It won't do that.
Okay, I try to speak more clearly, and when I speak, I turn off my camera for a better connection.
Yes, that'd be good. Thank you. Yeah.
Thank you so much.
I'm still not seeing those two others, Brett Wilt, and I don't see.
No, I practiced with Brett yesterday, so he's hopefully he will join. And this, I think Sanling has something he won't be able to join early, so that may be why he's not here. Yeah, but Brett,
I expect he'll be here though.
Yeah, I think Brett knows, and hopefully. Maybe I'll just drop him. Maybe I will drop him an email quickly. I think
Say, Adam, if you want to go ahead and present and put your title slide up, that probably would be a good thing to do.
Sounds good. Let's do that.
which fire is it in your background?
That's the Langdon unit burn, and that's our prescribed fire from Utah National Forest from last year. Pretty big one as for a prescribed one.
Same, okay. All right, wow.
So it's 10:45. Shall we begin, Wei?
Yes, let's go. I'm still looking for the second speaker. Hopefully he'll be there before this talk finishes.
It looks like he's here now.
Oh, okay, good.
Very good.
All right, let's go.
Okay, welcome back, everyone. The first talk in this third session of the WRF MPAS workshop is going to be given by Adam Kochanski, and he's going to talk to us about modeling fire-atmosphere interactions with WRF S-fire. Go ahead, Adam.
Hello, welcome everybody. So let's get started. Today I will be talking about different types of fire-atmosphere interactions that we can simulate using a coupled fire-atmosphere model, WRF S-fire. And if you think about what is happening in the atmosphere once we introduce fire, there is a lot of processes that are going on at the same time. So you can imagine that you have really intense heat source here at the ground because of the burning fire. It induces this convective updraft. It induces this plume. As a consequence of that, you have some inflow into this convective column, so that will result in those so-called fire-induced winds near the surface. You will also have fuel moisture that will be changing depending on atmospheric conditions. You will have some mixing because of the plume, and then the plume itself will interact with microphysics. It can potentially interact also with the chemistry in the atmosphere. And on top of that, even if you think about simple things like radiative impacts, you will have the solar radiation that will be blocked by the smoke column. So you will have some smoke shading effects and all the consequences associated with that. So basically, there is a lot of things that you can potentially investigate and a lot of processes that are going on at the same time. And using a coupled fire-atmosphere model, we have a chance to investigate at least some of them. So before I go into the actual examples of that, just a quick note about WRF S-fire history. You may be wondering, okay, there is WRF fire, what is WRF S-fire, what's the difference between them? And basically, everything started early as WRF fire code. And basically, after adding the WRF fire code to the official WRF repository, at some point we had to diverge a little bit, and at that moment the older version of WRF S-fire that was at that moment named WRF fire was then maintained by NCAR, and in parallel at the same time the newer and updated version called WRF S-fire was being developed by mostly Jan Mandel from UC Denver and in general Open Wildfire Modeling Group. So we kind of started in parallel doing different things with the model, and that's why it diverged over a couple of years. So what we try to do is just from time to time migrate some of the capabilities from one model to another. We pull from generic WRF repository, trying to be up to date with all major releases, but also if we add some new big important components, we try to port them back to WRF fire. So that's how the fuel moisture model got into WRF fire, for example. But the good news here is that in a WRF S-fire code, we actually have both codes. So if you get the code from our repository, you will have an option either to use WRF S-fire, and you will be just activating that with iFire1 option. And if you want to use WRF fire version, you can use the same code and you will just activate it by using iFire option 2. So now let's get to the actual topic of this presentation. So those fire atmosphere interactions. Of course, in order to capture those interactions, you need to have modules in place that would resolve the physics associated with these processes. And in the simplest case, if you think about WRF S-fire or WRF fire, of course, you will need the WRF atmospheric framework, but it's going to be linked with the fire spread model, something that computes how fast the fire progresses through the landscape. It will be coupled also with the fuel moisture model and some emission model, so you can compute how much smoke is being emitted. Now, if you want to do something more advanced than that, you can use also coupling with WRF Chem. And in this case, the structure is going to be very similar, but on top of those regular boxes that you saw before in the regular WRF fire or in WRF S-fire, you will also have WRF Chem. So basically, in this case, we will have interactions between the fire and the atmosphere. We'll have interactions between the atmosphere and the fuel moisture, but we will also have a fire emission model that will be computing emissions, and those emissions will be fed to WRF Chem, and WRF Chem will be integrated with WRF. So at that moment, you will be able not only to capture those interactions in a physical space, but also in the chemical space, and you will be able also to capture other interesting things like interactions in terms of the radiation, for example, between the smoke and the atmosphere. So if you think about those fire-atmosphere interactions, there are pretty much 3 different levels at which you can think about them. And there are 3 different kind of loops that allow you to couple fire to the atmosphere. And the loop number 1 is this, let's say, dynamical loop. So that's the loop that basically allows you to account for the fact that once you add heat to the atmosphere, you will have this convective updraft, and those convective updrafts are going to change local circulation. And as a consequence of that, local winds interacting with the fire will change as well. So you have those fire-affected winds because of the heat and moisture flux computed by the fire spread model, and that's like loop number 1. Now, the second loop is the loop number 2, and that's the loop through the fuel moisture model. So you can imagine that you have changing weather conditions simulated within WRF, and those changing fuel moisture conditions, atmospheric conditions, will then translate into changes in the fuel moisture, and this fuel moisture changing will interact with the fire spread model. It will impact how fast the fire propagates, how much emissions we have. So that's going to be the second loop through the fuel moisture. And then the third one is through those emissions and within the chemical framework of WRF Chem. So you can imagine that here you will have smoke, and this smoke will have certain radiative properties. Those radiative properties will also change local meteorological conditions, and those local meteorological conditions will then feed into the fuel moisture model, into the fire spread model. So everything will be coupled. So those are going to be 3 levels of coupling that I will be talking about. So the very first one is this dynamical coupling because of the presence of the heat near the ground. And here is just an example of the Fireflux 2 experimental burn on the left side, and on the right side, that's just a simulation done with WRF fire. And the interesting thing here is that we have the tower placed here on the plot, and we can measure wind speed and temperatures at multiple levels. And if you look at what is happening, as we have fire approaching the tower, you see those hotter colors. Those are the temperature plotted here using the color scale. So here's the hottest point corresponding to the fire front. If you zoom in, you will notice a very interesting thing, which is that during the fire front passage, actually those winds close to the surface are faster than what happens aloft. And the reason of that is this convection into the convective column induced by the fire itself. So that's this coupling because of the heat and the pyroconvection induced by the fire itself. Now that translates also into like the spatial distribution of winds. And here on the right side, you see all those orange regions, and they correspond to the places where you have stronger winds because of the presence of the fire. So here on the left side, that's a simulation that ignores the coupling between the fire and the atmosphere. And on the right one, on the right side, you see the one with the full coupling, and you see that the behavior of those 2 fires is different, but also variability in the winds in the coupled framework is much higher. So those are the things that you can investigate using a coupled fire atmosphere model. Here is another example of LES simulations for the Fireflux 1 burn. And here on the top, you see just a footage from the fire itself. And here was roughly the location of the tower that was instrumented with multiple anemometers and thermocouples. And then if you look what is happening in terms of, for example, vertical velocities, you can actually sense and you can sample by those sonic anemometers what was the local microenvironment during the fire front passage. And here on the top graph, you see the vertical velocity at 2 meters above the ground. And those circles, those are the values from the model. And those dashed lines and solid lines, those are filtered and unfiltered data from the sonic anemometer. And if you look at that, you will see right away here this updraft associated with the presence of the fire itself. This updraft is even higher, it's stronger if you look higher, if you are higher up at 10 meters above the ground. That's what is shown here on the plot below. And if you think about it, that's the indication of the updraft. You see those vertical velocities, the positive values, and then you also see the downdraft. And those are the negative values associated with the inflow into this convective column behind the fire front. So it's not that we care just about those vertical velocities, but at the end of the day, we are really interested in horizontal winds and how those vertical velocities and the updraft controls also this inflow in the convective column and surface winds. And that's what you see here. So very interesting thing. During the fire front passage, you have very significant acceleration in the winds. We are talking about 3 meters per second going up to 10 meters per second at just 2 meters above the ground. And at 10 meters above the ground, it's a smaller, but still significant increase from something like 4 meters per second to 8 meters per second. So that's the very first thing. Now, the second one, let's talk about the fuel moisture and what the fuel moisture does. So on this figure here on the right side, what you see is a time series of the fuel moisture. That's the purple line. And here are the values on the right side. And the fire area is here plotted using this red line. So you see this almost like stepwise character of the propagation of this particular fire, and it's associated with those fluctuations in the fuel moisture. So when the fuel moisture goes up, you see that the fire is stagnant, and then when it goes down, it starts going. And you will see the same thing on the left side. Here, this field at the bottom, that's the color-coded fuel moisture with hot colors corresponding to dry fuels and those cold colors going into bluish for the moist fuels. And as you start thinking about what is happening here, you will notice that once we start those simulations, we will have increased fire propagation during the daytime when we have lower fuels, and that's also when we will expect a lot of smoke. And during the nighttime, we will have reduction in fire activity, and we will have less smoke and slower growth of the fire itself. So if you think about what it does to the plume rise and the plume dynamics, it's really important. And on the left side, what you see here, that's the simulated plume top height. And you see how it fluctuates. It goes from something like 1 kilometer up to over 3 kilometers. And those changes are associated with those variations in the fuel moisture. And on the right side, what you see here is just the time series. And this time series is just showing you how we did in terms of the plume top height compared to the miser, which are those points. And that leads me to the last one, the last coupling mechanism, which is through the Chem. And here you see that's the simulation of 2015 California fires. And you actually can even notice the stagnant smoke in the valleys that is almost trapped, and it just keeps staying there. And the reason for that is that the smoke itself reduces temperature near the ground, and that's what you see here on the plot here. And it increases a little bit temperature aloft. So overall, it increases atmospheric stability. And then what happens is that we have more smoke in the atmosphere. And as we have more smoke, we'll have reduced solar heating near the ground. And that's what you see here. That's up to 500 watts per meter square. That in turn is gonna reduce surface temperatures by up to 3 degrees of Celsius. That's gonna limit the vertical mixing, and it's gonna lower surface winds. That is going to translate into shallower PBL height, and then we will have even more smoke and higher concentrations near the ground. So that's another third coupling loop, as you wish, captured within the WRF fire model. So basically, just to wrap up, those are the 3 different loops that we have within the WRF fire. We have fire-induced winds and fire convection. We have loop through the fuel moisture, and we have fuel loop through meteorological impacts of fire emissions. And that's everything. I'm ready for your questions. Thank you.
Well, thank you, Adam. There was a question in the chat that's already been answered about the version of WRF being used, and people can look at the chat for the answer to that. Another question that came in is, what are the initial conditions for fuel moisture?
So there are 2 different ways how you can initialize fuel moisture. So number 1 is you can assume that the fuels are in equilibrium with atmospheric variables. So you will use equilibrium moisture content to initialize your fuel moisture model, or you can use a fuel moisture data assimilation system. And that's what we have within WRF. So we assimilate surface observations from remote automated weather stations hourly. And we combine that with the fuel moisture model to get fuel moisture analysis. And those spatial maps are then used at the beginning of each forecast.
Okay, and the almost last question is, what is the scale of the fire that was simulated? And that came in right at the end. So that was probably that last simulation you showed.
So the last simulation, the one for all those multiple fires in California, that was run at 1 kilometer resolution. That was the innermost domain, and the fire itself was traced on, I think, a 60-meter resolution mesh.
Okay, and the final question is, what prevents S-Fire from becoming part of the official WRF code base?
Well, basically, as we can diverge at some point, at that moment, we have conflicting modules and we do things differently. So it would require pretty much significant effort to kind of port everything that we added after 2011 and to avoid conflicts. And that's kind of the difficult part here.
Okay, understood, yes. Okay, let's move on to our next talk. We're going to hear from Brett Wilt. He's going to talk about IBM Graph and give us an update and a roadmap. Brett, if you want to take it away.
Yeah, thanks, Bill. Let me share here. Okay, does that show up?
Yes.
Good. Okay, so I'll go through this quickly. I'm going to skip some slides to get through this, but I just want to give a sort of a really high-level overview of, I guess, our accomplishments going back in the last year, and especially our goals for this year and moving forward. Again, we do have an MPAS application here since about 2019, I think, that we implemented to drive a big chunk of our weather business. I really need to give credit here to a lot of different people and different organizations. You can see my team here below. Very good people at what they do, and I could not do this without any of those people. But I really want to call attention to some of the organizations, especially NCAR and NVIDIA, that we've been working with the last 2 or 3 years. And really kudos to IBM, because none of this could be possible without their continued investment into some of the hardware that you'll see here soon with our expansion plans. So just a really a quick update going into last year. So on the right here, you see we basically have 3 graph application or 3 MPAS applications currently. We have an hourly graph that runs out 15 hours at 3-kilometer resolutions in those refinement regions in this top map here. And basically, we initialize with a T-6 eSIMWF analysis, and then we run GSI data assimilation at this point, just surface data only. We basically halted all GSI development because we knew we were be moving towards JEDI since last year. So that's in progress. We do assimilate US NextRad radars for cloud analysis, and we have forecast streams to available customers down to 5-minute intervals. This mesh here is about 24 million cells, so it takes about 51 nodes to process this in time within about a 45 to 50-minute time period. 51 levels, and just for anyone who does use MPAS, so we were able to get about 10 DX use out of according to Bill's recommendations, with the number of acoustic substeps equal to 4. We were able to go from 18-second to a 30-second model time step to save a big chunk of time computing there. Our second one is what we call Graph LR. It's basically just a CONUS and YERP run that's run 4 times a day. This run goes out 72 hours, and it drives most of our media clients. And as you'll see here soon, there's always both Graph LR and Graph are available to media clients, but since Graph is limited to 15 hours, its overall use is quite limited. So most people use Graph LR. And then finally, MPAS 15 kilometers, the uniform 15-kilometer mesh, and it's updated 4 times a day as well. This one uses a GFS cold start analysis. And this is primarily for aviation customers regarding turbulence products, as well as a backup system if we have failures on Graph or Graph LR. On the left-hand side here real quick, one of the things that we basically launched Graph in 2020 as far as making it available to media customers. So we had this 1-year time period where we had parallel data with our previous WRF system we called RPM. Initially, we were quite deficient in our performance regarding some of our metrics like 2-meter temperatures and precip scale. So it took over nearly a year to work through some of those hurdles and having superior forecast data, and we were able to accomplish that as of September 30th of last year. And that's when we officially terminated RPM and we're fully based on Graph now. How did we do this? We really listened. One of the advantages we have is customers all throughout the media clients that when our forecasts are bad, we know it very soon. And but it's also an advantage for us to have a group of guys that and ladies get together here on a 2-week schedule where we go through some of the case studies that they bring to us with some of the issues that we see with Graph at times. So I won't go through the quotes here, but obviously there was a lot of hesitancy in the beginning. No one likes change. So when we went from RPM to graph, a lot of complaints with forecast skill, and we overcame those through feedback from a lot of those customers. And the nice thing is a lot of those customers really felt empowered to have an impact on the model development. So that communication channel is quite vital to our business. Just one quick example, I worked with Mark Nelson regarding shallow cold air issues and snowfall across the Columbia River Basin at times. This is an example on the left-hand side showing a graph forecast the day of that had snow, did have snow across the Columbia River Basin. The day before graph had nothing across that area. And then on the left here is the day before forecast. And then on the right here is after some of the developments related to PBL physics and orographic wave drag, we were able to build that snow in. And with another number of lab cases that we ran, we were able to implement that operationally. I'm going to skip over some of these details here, but again, the media clients allow us to give feedback regarding wind forecast, wind gusts. Here we have examples of fog forecasts and initially complaints that we made improvements with that. Obviously, freezing rain events and the snow issues during the wintertime. This was related to the common issue with NOAA that basically accumulates freezing rain as snow, and that ended up corrupting the forecast and having widespread freezing rain where areas that should not have been. So that feedback allowed us to make that change quite quickly, and we had that change within a week operationally. So it allows us to be very flexible in that way. I'm very active on the social media side of things to see what the customers are saying. So there's a couple examples of things that are not good comments. So those type of comments are quite valuable to us. So we kind of grab onto those as quickly as possible and engage the customers so we can move forward with some case studies and see what could be going on in these cases. A whole host of model updates over the last 2 or 3 years to overcome some of these deficiencies. We'll skip through the details here, but some of the big ones, some cloud effective radius changes, more similar to ESON-OVF model. We're using the Thomson cloud fraction, WSM microphysics, several changes there to increase our precept scale over the last few months. Again, YSU PBL, and then the scale over convection, thanks again to Wei Wang in the beginning to help us out to get this implemented. Continue to tune that, and we're getting quite good results now. So where are we going into 2022? We really feel like we have the foundation now. Data assimilation has not historically been an active project here at the weather company, but we're quickly moving down this path to become more of a mature global type data center. And again, we have the foundation raised. We have a great model behind us now and great metrics showing the forecast skill. So we're really excited to jump into the JEDI world, and we've actually been working on that over the last 1 to 2 months. We are going through an OS upgrade on our cluster, so it's slowing things down a little bit right now. But we are moving forward with that, and what we're really interested in is being able to attract unique and proprietary data sources. One of those we've discussed before is sulfur and pressure data. There's a whole host of other type data observations that we could potentially use within JEDI and have a global impact in graph. So we really need to prioritize our business impacts going into 2022. And one of our biggest metric to move business in our world anyway is a short-term precipitation scale that drives a lot of our phone applications with Apple and Samsung, especially a whole host of B2C type clients. So why are we getting into JEDI data assimilation? Just showing this graph, this is going back since we started keeping track of equitable threat score relative to her. We really use her as a benchmark here, not necessarily competing with her, but we use a benchmark to know, to keep us, what's good and what's not, how are we doing? So going back to February 20, you can see in the dark circles there, what really stands out is during the stratiform type environments, graph is very, very similar to her and occasionally beats her over a 1 week time period, especially during the fall and winter months. But when we get to the convective season, because of our lack of a data assimilation system, it really hurts graph. You can see once we get into April and May, graph scale historically over the last 2 years has really dropped off relative to her. And that's something we're really focused on going forward here. I will say we had some spring updates here, like I mentioned with WSM6 to help with the short-term precipitation. And you can see at least this latest 3 months period of April, May, and June of this year, That drop-off has not occurred this year yet. So we're hoping that some of the changes that are really starting to stand out now to really help us out relative to the short-term precipitation scale. This is what I'm sure this plan will change, but this is where we're initially headed towards as far as development, is to have sort of a two-prong data assimilation aspect here. So one of them will be, we're planning to run 12 to 20 kilometer graph ensembles. This will probably be probably 20 to 30 member initially, and we're going to let that ensemble run and generate the perturbations, and then that will tie into sort of a hybrid ENVAR here ultimately. We're working on the static component of that already. We already have the forecast run over a 3-month period to generate the static error covariances. And then we'll incorporate that high-res deterministic 1-hour forecast to be able to keep some of the integrity of the convection when we tie all this together going forward in our ultimate hybrid ENVAR system here. Okay, how do we accomplish all this with the data assimilation? We need to make up about a 5x computational time here. So we're basically taking our two meshes you see on the left here, the hourly graph and the graph LR, and sort of merging into a unified graph mesh that's going to update 24 times a day. So basically an hourly forecast that goes out to 72 hours. And that will be driven by JI data assimilation, the hybrid ENVAR I mentioned. You can see that's sort of a preliminary mesh design that we have in place. We're in the process of working on that currently. Basically, we've dropped some in the Middle East, and especially South Africa and South America. We're dropping that, but we also increased our global resolution on the outside of the refinement region, so 12 kilometer, and then still maintain 3 kilometer over the refinement regions. So that allows us to make up about 2x there, given the reduced number of cells. And then finally, we need more computational resources, and that's where IBM comes in handy here. We're going through an expansion approval process right now, but our plan is to basically triple our graph compute capacity, going from about 81 GPU nodes to about 236 GPU nodes. We estimate about 180 of that would be used for this unified graph, hourly out to 72 hours. And then about 30 GPU nodes will be used for graph DA and the ensembles and things of that nature. And then we maintain 26 for research purposes. So yeah, we're excited about that. We're going through the upgrade process right now related to Red Hat 8.4. We're running into some issues with the latest NVIDIA compilers and runtimes, but there's always the details to be worked out. Finally, last slide here, but really we have a number of media requests for new products, cloud products, fair weather products, and ability to be able to get point data queries through graph. But overall, our market here is really in the B2C and especially the B2B going forward, where we're always looking to expand graph business opportunities. So some of the ideas that we've already had interest in is using graph as input to fire risk models. There's also always good business value in engaging the airline industry, especially with some of the flight optimization paths. We're working through that. But also from the B2C side, just a general experience from the user side, from the iPhones and Samsung applications that see future radar and how that relates to overall well-being on society. So we're excited. That's a quick update. So I guess we'll take questions.
Thank you, Brett. That's a very ambitious roadmap you sketched out there. And your meshes really show the flexibility of MPAS for sure. There's a couple questions in the chat. One related to one I was thinking of is do you run in the open source version of the MPAS GPU for graph, or have you tuned it yourself?
We're on 6.3, and obviously we have made several changes. Some of that does get fed back into NCAR's repository as needed. Some of it does not, because it doesn't make sense to make some of these changes and apply, because it's sort of unique to our application, like our initialization data and our data assimilation that's sort of really tuned to that. So where we can, we contribute back things that make sense.
Right. And the next question is, are there any plans to expand to air pollution predictions?
Not at this point. We have not gone down that route.
Okay, I'm not seeing any other questions. There's one more. Any thought of producing probabilistic forecasts and ensembles as opposed to ensemble just using ensembles for DA?
Not necessarily from the data assimilation aspect, but we do have probabilistic type products on the horizon here once we get to the hourly 72-hour forecast, because that'll really help drive some of those products and seeing how each cycle relates to the previous cycle.
Okay, thank you, Brett. Moving on to the next talk, we're going to hear from Olafur Rogvaldsen. I think I hopefully said that close to correctly. And he's going to talk to us about weather on demand.
Hello, and let me see if I can share the screen here as successfully as last time. Okay.
Very good. Take it away.
This is popping up. Great.
Yes.
So, open the clock. Well, nothing is done in vacuum, and I certainly did not do this alone. So, listing just a few of my collaborators: Joao Hakarot and Karolina Stanislavska and Jorge Rosas Santana. Quick outline. Just give you overview of the forecasting system we have been designing over the past 10 years or so, followed by our design philosophy. And the bulk of the time will hopefully be spent on showing you some interesting applications and in particular our ongoing endeavors with data assimilation, 3D VAR and 4D VAR with the original model. So the WAT system, it's a distributed system for not just running the Dwarf model, but also for gathering upstream weather data, both model output and observations. And this data can then be used to trigger scheduled or on-demand Dwarf forecasts. We are implementing the Dwarf Chem model, currently the version 4.3. We have not yet updated to the 4.4. And we can run the model with or without 3D or 4D VAR, or a mixture of 3D and 4D VAR data assimilation. I'll get into more detail on that later on. Now, the output data and also basically the upstream data can be processed for medium to long-term storage. And these results, so both observations and forecasts, are then made available to our customers through APIs, wide range of APIs. And the system is also quite frequently used to basically feed into a secondary or third-party decision support tools. So we can use it to run like hydro model, for instance. Sorry about that. Where, oh crap. What? What on earth happened? So can you hear me?
We can hear you and we're seeing your screen again.
Okay, good. So interestingly, if your iPhone rings, things do not go well. Okay, yeah, sorry about that. I think we were here. So yeah, built around the Dwarf Chem model. As I mentioned earlier, the initial data we can use both, well, most of the, or all of the global models from NOAA, so the CFS, GFS, and all the global ensemble members as well, and also the regional RAP model, the coarse outer domain of the RAP model. The code is stored in GitHub, and installation takes typically less than half a day. So in 4 or 5 hours, you can set up the whole system in a new cluster. And we have been using this to create what I would call conventional short to medium range forecasts. And this can also be used to scale down long range CFS forecasts. So we are doing up to like 45-day simulations for the South America at the moment. And so the philosophy is, in short, it's open source. And mainly, well, basically open source tools, we found them to be of sufficient quality, basically. And this also frees us from kind of risk of both vendor lock-in and also of having to pay fees for software libraries that we have very little control over. And this in turn has led to a quite resilient and scalable system, this philosophy of design. A few applications. Our main operation is in South America, focusing on Brazil, both for medium to long range simulations. This data in turn is used by a local company in Sao Paulo to run their energy trading services, renewable power production forecast, both for solar and wind energy. This is used as input to hydropower. So using both the downscaled forecast from Dwarf, as well as kind of post-processed data from the GFS and GEFS system and ECMWF as well. And most recently, we've been kind of dabbling a bit with agro commodities, both for droughts and also frost forecasts. Now, we introduced 3D VAR and 4D VAR data simulation to the system about 5-6 months ago, after having investigated back in Iceland. So this is the observational network in Iceland. We have about 260 stations. 2/3, we can say, are lowland, and a third of them are in the highland or at altitudes above 200 meters above sea level. And we have been having for many years now, we know that the Dwarf model has a cold bias for Iceland, certainly. And here's a kind of typical three-day simulation forecast over 1 year. So the first 6 hours are chunked here together, 6 to 12, 12 to 18. So basically day 1, day 2, day 3. And there is a consistent cold bias, which kind of increases a little bit as the forecast goes on. So last fall, we started trying 3D VAR simulations, and the initial tests were quite promising. We were kind of getting things are heating up. This is just a quick picture showing the difference between a simulation using data simulation and no data simulation. So it's in general, it's a bit warmer than the control forecast. So we've now been running this kind of system in 3 configurations for 4 months. So basically our control simulation at a 2 kilometer, 8 and 2 kilometer simulation resolution. And then we have one configuration where we use 3D VAR for both the outer domain and the inner domain. And then we have where we use 4D VAR for the outer domain, but for the sake of saving up computational power, we only use 3D VAR for the inner domain. So we initiate at midnight and noon and do a 12-hour forecast. And this is the result. Sorry about the. So up here with red and orange, we have the control. Blue is the midnight simulation, and the orange is the noon simulation analysis. And you can see that both, so red and green are the 3D VAR, these guys here, and orange and brown are the 4D VAR, 3D VAR mixture. So just turning on the 3D VAR or 3D VAR, 4D VAR simulation is reducing the mean absolute error for both temperature and winds as well. And same goes for root mean square error for temperature and winds. And in general, especially for winds, we have the combination of 4D VAR and 3D VAR outperforming the pure 3D VAR configuration. The only difference is in the bias for temperature. So here we have the 3D VAR, pure 3D VAR is slightly outperforming the mixed 4D VAR, 3D VAR, both for the 12Z analysis and also more pronouncedly for the midnight analysis. But all cases with 3D VAR or 4D VAR, regardless how we mix it up, they are a considerable improvement to the control simulation. And but for the winds, we have again the 4D VAR, 3D VAR is I would say slightly better than a pure 3D VAR, although it's not as pronounced as the mean absolute error and the root mean square errors. So to summarize, and again, I apologize for the hiccup earlier. So we have created a forecasting system that can be used to create conventional short to medium range weather forecasts, as well as downscaling of subseasonal simulations. And this was originally designed to meet the needs of national meteorological hydrological services that did not have much resources and maybe limited experience in running operational forecasting systems. So this has always been the idea that this could be set up elsewhere and run with minimum know-how of atmospheric modeling and hardware systems. So it's open source, event-driven, scalable, and resilient. And currently the use of variational data simulation is showing quite promising results. And of course, the output from the weather model can be used as input to a variety of other decision software solutions. So thank you very much.
Okay, thank you. I'm curious, with the Iceland data simulation experiments you were doing, do you know what observations were most important to improve, to show the improvements in the forecasts?
We are using basically everything that's available on the GFS website, so the radiance data and the buffer files as well. And then we have, in addition, the surface observations. We have not done sensitivity tests like skipping the surface observations or skipping the radiance data, sorry, for that.
Right, and was the verification of that done with those same observations ultimately, or?
Yes, yes.
Okay.
It's in a forecast mode, of course.
Right, right.
But I should mention that we are still using the background covariance error matrix. We are still using the default one. So we have not not yet gone into the work of creating our own custom-made covariance matrix. So that's kind of the next step along the way.
Okay, and there is a question that's come into the chat. What size of the OBS data have you used in your data simulation? And
yeah, basically,
and maybe more importantly, the time used for the 3D VAR and 4D VAR, the time windows.
The time window for the 3D VAR is ±3 hours, I believe, and the same goes for the 4D VAR. So it's a 6.
Yes, very good. Thank you.
And we are using a quality assurance system, so to kind of make sure that we are not getting any obvious rubbish observations in.
Okay, and there's a qualification to the question that came in, or a clarification. The person posing the question actually meant, what's the computational time or cost for this, for the DA compared to the forecast?
The 3D VAR is very limited. So it's I would say maybe 3 or 4 minutes for this 2 kilometer domain is 350 by 250 points, around that order. The 4D VAR is, as we are only doing it on the 8 kilometer grids, which is still 150 by 150 points, but that's maybe 15 minutes. So there's a reason we did this kind of trade-off. We also have an option where you just use nest down to go from the initial data created by 4D VAR to use nest down to recreate the input data for the inner domain, but we've not been testing that as thoroughly as a 3D VAR option.
Okay, thank you. And thank you for your talk. Moving on, our next talk is going to be given by Jorge Humberto Bravo Mendez, and he's going to talk to us about WRF MPAS used as operative model for small centers of meteorology. So if you'll share your screen, we can begin.
Hello, hello. Can you?
We can hear you. Somewhat. You've frozen. I think maybe your connection. Uh-oh. I think.
Hello, 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 hello. Can you hear me?
Yes, we can hear you.
Oh, sorry, I have some troubles with my internet connection. I will try to speak quickly and show my presentation. Can you see my screen?
Yes.
I will turn off my camera for a better connection. So, hi everyone. First of all, I want to thank the opportunity to be part of this WRF MPAS Users Workshop. Today I will speak about how I use the WRF MPAS models for regional or local forecasts with operative purposes. Introducing myself, my name is Jorge Humberto Bravo Mendez. Sorry, can you see my screen?
Not yet, but it's trying. There, we can see your screen again.
Okay. Again, my name is Jorge Humberto Bravo Mendez. And I'm a master degree in hydrometeorology. The last 8 years, I worked as climate researcher for the Secretariat of Civil Protection of the Veracruz State. I'm Please, can we pass the next, and I will try to show my problems.
Okay, well, Kelly, shall we move on to the next talk then?
I return after, please. I return after the next talk, please.
Okay, so David, are you there? Okay.
I am, yes.
Yeah, can you give it a try?
Okay, so the next talk is going to be given by David Ovens, and he's going to talk to us about the cold bias problems over lowland snow using the NOAA MP land surface model, and is going to demonstrate the problem and hopefully show us how to solve it. Go ahead, David.
Okay, thanks. And good luck on the next, the previous speaker getting that fixed. So yeah, this talk will address the cold bias problem that we've noticed over lowland snow using the NOAA MP land surface model. And yeah, hopefully I will demonstrate the problem and provide possible solutions. This is work done by myself, David Ovens, and Cliff Mass at the University of Washington. So this past winter, our real-time 4-kilometer WRF runs forecast extreme cold that was especially unrealistic for Western Washington lowlands. This plot of 2-meter temperatures for a 12-hour forecast valid at 12 UTC, 4 a.m. local time on December 28th, 2021 shows many dark purples and verging toward whites areas that represent temperatures below 12, below 10, even into the single digits. However, the observations show temperatures that were in the low to mid 20s. The overall verification for this forecast is shown here with larger circles representing larger errors. The blues show model forecasts that are too cold, and the reds and browns show model forecasts that are too warm. Domain-wide, the 2-meter temperature bias, model minus observation, is minus 5.65 degrees Fahrenheit. As you can see, there are many sites with large blue circles representing a forecast that was over 10 degrees Fahrenheit too cold. As we saw in the previous slide, the Puget Sound region of Western Washington had several sites with temperatures forecast as low as 5 degrees. Puget Sound is up in that area. This is a plot from our 4-kilometer WRF ensemble forecast system. Each line is a separate ensemble member, and observations at CTAC are in these orange circles. CTAC is this red dot here on the right. Several ensemble members use different physics suites, but most use a common physics suite coupled with initial and boundary conditions that we take from a variety of global models. The standard suite of physics options that most ensemble members use has been shown over many years of operational use to perform quite well for our region. You can see that many ensemble members were over 10 degrees Fahrenheit too cold, and even as much as 17 degrees Fahrenheit too cold in the initial hours. In this highlighted area, however, you can see that 1 or 2 members provided relatively realistic forecasts. All of the ensemble members with unrealistic extreme cold forecasts for this case and other cases we've observed have 2 things in common. Snow cover, as depicted from this case here on the left, and the NOAA MP LSM, which brings up some questions. Why is there an extreme cold bias when using the NOAA MP LSM during winter periods with snow cover? Are other LSMs better? Can NOAA MP performance be improved with the right settings or physics options? Though we don't have time in this talk to address all of these questions, we will focus on this last one, and at least we'll explore the performance of some other LSMs over our region for this past December and January. First, looking at this 28 December case, it is clear from these 2 WRF forecasts, which are identical except for the land surface model used in each, that NOAA MP on the left is far colder than the NOAA on the right, far less light purple in Western Washington with NOAA, and the white colors representing temperatures of -10 degrees Fahrenheit and below are far less prevalent in NOAA. Plotting the differences, NOAA minus MP on the right now shows many locations warmer in NOAA, with reds being 1 to 5 degrees warmer, greens, as seen in the lowlands, 5 to 10 degrees warmer, and even into the browns, which are 10 to 20 degrees warmer. Lots of greens in the Western Washington lowlands, but note that the Cascade Mountain Range, which runs through here, is mostly white, and actually there's not much difference between NOAA and NOAA MP. So verification for is shown here again. This is the same plot we saw earlier for NOAA MP with 2 meter temperature bias comparisons. And the domain average bias for NOAA is about 3 degrees Fahrenheit better, with -2.66 for NOAA versus that -5.65 we saw for NOAA MP. And as highlighted here, there's a dramatic increase in skill over Western Washington lowlands, with NOAA eliminating nearly all of the large blue circles, again showing areas that were 10 degrees Fahrenheit too cold, and the next smaller blue circles, which were areas between 4 and 10 degrees. Though NOAA does seem better for these snow cover cases, we run forecasts year round and have found that NOAA MP is quite good for most other situations. Should we just abandon NOAA MP for another LSM during winter, or could we find a way to use NOAA MP and improve temperatures over snow cover? To try to answer this, we started experimenting with physics and NOAA MP nameless options to lessen the cold bias problem. Our ensembles provided a good starting point for these experiments, since we already had a couple with relatively good forecasts. Something they also indicated is that I should start by attempting to address this rapid extreme cooling that happens with the NOAA MP. After examining statistics from several cases, I determined that using our 12-kilometer domain and all of the observations within it would be sufficient. So I ran multiple experiments to improve our cold bias over snow. Our real-time, uses WRF ARW version 4.1.3, but these tests were conducted using 4.3.2. I tested RUC, NOAA, and NOAA MP LSMs. For radiation, I used RRTMG and Goddard. And based on NCAR's Antarctic prediction system settings, I even mixed the Goddard shortwave with the RRTMG longwave. For the surface layer, I used the revised MM5 Monin-Obakov, the MYNN, and the old MM5, option 91. For microphysics, there were Thomson and Thomson aerosol aware schemes. PBL schemes were the YSU, as in our real time, and the MYNN 2.5 level TKE. I tried various NOAA MP code modifications to limit the effects of snow on temperature, and I'll discuss these later. I tried various nameless options for the NOAA MP, though those quickly revealed no significant change in 2 meter temperatures over snow. As I iterated through all of these experiments, I arrived at a tuned snow, or T-snow configuration, which is a set of physics options, code mods, and pre-processing for use with NOAA MP. In the interest of time, I'll only summarize these here, and we'll go through these rather quickly. For physics, these are the choices that led to the best improvement in 2 meter temperatures over snow. The MYNN level 2.5 TKE PBL, Goddard shortwave combined with the RRTMG longwave, the old MM5 surface layer, option 91, and Thomson aerosol aware microphysics. The NOAA MP code mods are all an attempt to limit the effect from shallow snow. I used the Verseggi 1991 snow thermal conductivity code, but I limit it to be less than or equal to 0.25. I require deeper snow depth of 15 centimeters versus 5 centimeters in snow surface temperature and ground snow cover fraction calculations. I also set snow depths and water equivalent to 0 for larger values than the defaults. I also perform a pre-processing step to limit the effects of fresh snow on warm ground by setting physical snow depth, snow water equivalent, and the snow cover fraction to 0 when the topsoil temperature exceeds 0 degrees Celsius. And again, that's looking at WRF input files. These bar charts represent the mean error on the left and mean absolute error on the right for 62 cases run from December 1st, 2021 through 31st of January, 2022 for all stations within the 12-kilometer domain. NOAA MP with our standard physics options is in blue, NOAA is in orange, RUC red, T-SNOW is in green, and also shown is our MM5 Eta in purple. At 12Z, corresponding to overnight low temperatures, other LSMs perform better in mean error and mean absolute error than the NOAA MP. At 0Z, corresponding to our daytime high temperatures, NOAA is actually worse than NOAA MP in both mean error and mean absolute error. But again, T-SNOW, which uses NOAA MP, has the best bias or mean error and is just slightly less skillful in mean absolute error than experiments using the RUC LSM. Taking 0Z and 12Z in combination though, T-SNOW is the top WRF performer and is even on par with that venerable old MM5 Eta. So that's another story. Again, these results show 2 months worth of statistics for forecasts with varying degrees of snow cover. But how does T-SNOW do for our 28 December case in Western Washington? Well, to illustrate this, I ran experiments down to 4 kilometers for these to compare to our ensembles. And here's what we see. Again, NOAA MP is the thick blue line down here, diving down to this cold temperatures. NOAA is the thick orange up here. RUC, the red, and T-SNOW is this thick green. And again, the orange circles represent the OBS. You can see that with T-SNOW and the other LSMs, we are able to mitigate the problem of rapid cooling and better track the actual observations. In summary, we have seen that NOAA MP exhibits a cold bias over snow cover. Other LSMs are better at predicting 2-meter temperatures over snow, especially the overnight low temperatures. NOAA MP 2-meter temperatures over snow can be improved by choosing different physics, using some NOAA MP code mods, and removing some snow inputs when top soil level temperature exceeds 0 degrees Celsius. With that, I would like to conclude and hear your questions or suggestions from people. Thank you.
Thank you, David. There are a couple questions or a comment and a question in the chat. The comment is from Wayne Angevine pointing out a paper he suggests you might want to take a look at. Then there's a couple of questions popping up. First, are there any plans to implement these modifications as a separate parameterization or something of that sort in the WRF repository?
Well, I think I'd love to see input from other folks from NCAR to see what they think about this before doing that. I am implementing it as an ensemble member. I've been doing that since either February or March of this year. So I'm going to run it for at least a year as part of our ensembles and look at its statistics throughout the year.
Okay, another question is, do you still get improvements if you only make your NOAA MP mods, or is this a package?
Well, these, so I guess the question is, have I done these mods without NOAA MP? Was that the gist of the question? Because I did try these actually with the RUC and with the NOAA, and they make slight improvements. Obviously, there's no, I didn't do any code mods to the RUC or the NOAA code, but actually using these physics packages with snow did make slight improvements to those other LSMs as well.
Okay, next question is the cold bias sensitive to the PBL schemes?
Well, it does have there was a slight improvement. That's why going from the YSU to the MYNN was a slight improvement. I had some other slides showing what the YSU and the NOAA MP do to the vertical profile at CTAC, and there was this amazingly sharp, unrealistic inversion that was created with the YSU and the NOAA MP that I was able to mitigate by using the MYNN and or doing all these other modifications too.
Okay, there's a question here. What's the surface layer scheme within the NOAA MP? Not quite sure how to interpret that, but
yeah. Well, I know in Dwarf we're able to choose a surface layer scheme separately. Maybe the NOAA MP folks could. Yeah, the NOAA MP code, I got to say, was relatively difficult to figure out what it was doing to all the various things. So I jumped into the code to the places where I could understand where snow was and how that might be affecting these temperature changes. So I didn't want to alter how NOAA MP was handling temperature and radiation at all. I just wanted to handle what it was doing with snow. That's why I made these somewhat simple modifications. But yeah, in terms of the surface layer, I did try those 3 different surface layers, which are options. And again, going back to the strangely old MM5 surface layer, option 91, that actually seemed to make improvements.
okay, well, that's all the questions we have in the chat. I think perhaps we can attempt to circle back. Humberto?
Bill,
Yes.
I'm trying to start the presentation. Can you see anything?
I can see the slides, yes.
You can. Okay, good. Good start. Let me go to slideshow mode. You see it?
Yes.
Okay, I will mute and Humberto, you can start talking and let me know to advance slide for you.
Okay, thank you. Okay, can you start at the first slide, please?
Okay.
Okay, thanks again. First of all, I want to thank the opportunity to be part of this WRF MPAS User Workshop. Today, I will speak about how forecast with operative purposes. Introducing myself, my name is Jorge Humberto Bravo Mendez. I have a master's degree in hydrometeorology. The last 8 years, I worked as climate researcher for the Secretariat of Civil Protection of the Veracruz State. I am a member of REDESCLIM. This is the acronym of the Hydrometeorological and Climate Disaster Network. It's from Mexico country and with members around the country. I mention this because it's important. Next, please. In this image, I show my country, and in the red circle pointed with an arrow, where is located Jalapa, the capital of the Veracruz State. I live here. Next, please. The Secretariat of Civil Protection of the Veracruz State has the Center for Weather Forecast and Monitoring, which functions as a regional meteorological center, and it requires reports, bulletins, warning, etc. Next, please. So what's the problem? The free access weather forecast models outputs are good for a quick view, but its scale is large, global scale or mesoscale, so their cell grid is too large, and for a local forecast, it not works in my opinion, of course. And next, the Dwarf as solution. As all you know, the Dwarf is more efficient to install in a cluster or HPC, but also it's possible to install the model in a desktop or laptop, and the model will run fine. Also, it depends the region area extension and the cell size. It's also possible to use free access data as input data for work time data with better resolution, for example, 4 or 1 kilometer or more resolution. Significant research has been conducted in this area, and there is a lot of literature to learn Dwarf. Next, please. Here is a summary of how computers were improved to install and run the Dwarf in the Secretariat of Civil Protection, the most important in red. Currently, I have 2 workstations to run the models. And next, please. Now, how the operational Dwarf works. First, a cron job run twice a day, midnight, midday. It called a Python script, which downloads input data. When we have the run the pre-processing WPS and then the Dwarf, and we obtain NIT-CDFs. With this NIT-CDF, we need to change from vertical sigma levels to pressure levels, and I use NCL scripts, but currently I have some similar post-processing using Dwarf Python library. With the Dwarf output in pressure levels, I use Python. The image and GitLab pages, also I can use Facebook pages for host the web page. When the whole process is finished, a notification email is sent to the operational meteorologist so that they can review the Dwarf updates. Next, please. These are examples of precipitation, temperature, and wind map using the link. Next, please. I have 2 examples to 2 hurricanes during the 2017 hurricane season. In both cases, we obtained a good approximation of the accumulated precipitation 48 hours before the official report. This first is the hurricane category. Next, please. And the second, the hurricane category 1, Katia. Next, please. I know the Dwarf model is an unstable model and it's worked fine. I really like to work with the Dwarf, but I think, or maybe more correct in my opinion, the future of the weather models are with non-structural meshes like the M. With this structure, nested domain is not needed. You can increase the resolution on the same mesh, some similar as we can see in the MPAS logo. Here in the left, traditional mesh with a close-up showing 4-kilometer mesh, and right, hexagonal MPAS mesh with a close-up showing 3-kilometer mesh. Next, please. Examples of precipitation, temperature, and wind maps with MPAS outputs and the link to the website. The MPAS also run operative, but currently it's not running because we don't have storage. So you can see an old example. Next, please. Also, I work with Dwarf Hydro using different meteorological data to run the model, but the main data to run Dwarf outputs. For this example, I run the Dwarf with ERA 5 for a historical event in the Nautla Basin. But I use this same domain to run Dwarf Hydro Operative. Every day, the run model run twice a day. And you can see the web page following the link. And next, please. Currently, also, I try to create a web map drainage areas in the Veracruz state. And next, please. Well, as I mentioned before, I am a member of the RedSclean, a network related with the hydrometeorological disaster, and other members have asked me for help to install Dwarf. And here I show some support provided by me. Next. December 2019, collaboration with Dr. Enrique Souza, member of RedSclean, was built, and I was able to run the Dwarf model using resources from the Autonomous University of Querétaro. Next, please. So I have an HTML and CSS template to display an animation. You can next, please. November 2020, Dr. Julio Cesar, also RedSclean member from University Center of the Coast, was the one who suggested the meeting with the Municipal Coordination of Civil Protection and Firefighters of Puerto Vallarta, Jalisco. And during the 2020, based on the Dwarf model, was developed for the municipality of Puerto Vallarta, Jalisco. Next, please. I worked to install the model, but after some time they had some problems with their desktop and stopped using the Dwarf. Next, please. March 2021, also 2019 RedSclean annual meeting, the Municipality Planning Institute of Bahía de Banderas in Nayarit expressed interest in the Dwarf. This municipality, called Bahía de Bandera, is next to the Puerto Vallarta, but in another state. And in March 2021, I had the opportunity to visit their facilities to work on the model and train their staff. Next, please. The model is fine. In each case, you can go to the link and visit the web page of these places. Next, please. Finally, I recently traveled to Cozumel Island to install the Dwarf model at the Autonomous Quintana Roo University with the Dr. Frausto. Current. Next, please. The interest is to have operational forecast in advance of the rainy and tropical cyclone season to monitor and forecast the weather in the Mexican Caribbean. Next, please. In conclusions, it's not necessary a powerful machine to run Dwarf. The process can be automated and obtain operational forecast. Not only Dwarf, MPAS and Dwarf Hydro can also be used for operational purposes. And this process can be replicated at any weather center that needs higher resolution forecast. And next, please. And this is all. Any question, to be honest, I prefer to answer writing in the chat. Thank you so much for this time.
Thank you, Humberto. I do not see any questions in the chat yet. I'm just curious, are tropical cyclones the main forecast problem that you're trying to address in your work here, bringing WRF to the various applications?
I try to answer in the chat, if no problem. Yes. Thank you so much.
Thank you. Okay, for the last talk, Senmin He is going to talk to us about the brown carbon radiative effects over high mountain Asia, an application of the WRF Chem model. And you're sharing, I can see your screen and not your talk yet, but.
How about now, the first screen?
We're seeing the presenter mode. So if you can swap screens, you'll be there.
Let me see. Okay. Let me reshare that. Okay. Let me. Let me see. How should I do that? Let's do this. Okay, can you see my screen?
We can see your screen, yes.
Okay, now let's see how this goes. How about now?
Very good. Go ahead.
Okay. Yeah, hi everyone. So today I'm gonna talk briefly about our recent work on implementing a new important aerosol species called brown carbon into WRF Chem for application over the high mountain Asia. So what is the brown carbon? Just a little bit of background. It is a light absorbing organic carbon which can strongly absorb sunlight at the near UV wavelengths. It can cause the atmospheric warming, and once it deposits onto the snow pack, then it can reduce the snow albedo, which would accelerate the snow melting and also reduce the snow albedo in a large amount. So this is why we care about this specific species, particularly over the mountain snowpack areas, like our application here for the Tibetan Plateau and the Himalaya regions. Most of the previous modeling studies have focused on the other light absorbing aerosols like black carbon or soot particles and dust particles over the snow cover regions, but less is known for the brown carbon. So that's why we this is really motivates us to look at this species. And also in the current WRF Chem models, we don't have this specific brown carbon species represented by the model. So that's why we want to implement a whole life cycle of this specific aerosol species. So here is a general workflow of how we implement the brown carbon life cycle. So first we start with the bulk brown organic carbon primary emissions, which is already included or used by the WRF Chem using the prescribed emission inventories. And then what we need to do is that we need to calculate the brown carbon versus total organic carbon fractions at the emission, so that we can use the total organic carbon emission to calculate the primary brown carbon emissions from, for example, anthropogenic emissions and also the biomass burning fire emissions. And another source of the brown carbon is from the secondary organic aerosol productions, which we already have some parameterizations or processes to account for this, although there are still some uncertainties within this SOA production. And leveraging these existing total SOA productions, what we need to do is we just need to calculate the secondary brown carbon fraction inside within this total SOA production. Then we can calculate the secondary brown carbon production, and add these two new species into WRF Chem. Then we can follow the other aerosol processes to simulate the brown carbon transport and also the interaction with radiations, interaction with cloud, as well as a new process called photopleaching. This is because after the oxidization through the photolysis processes, the brown carbon could be photobleached, where it becomes the normal organic carbon in terms of radiative properties, so that it does not absorb the sunlight anymore. So we will also include a parameterization to account for this process. In that case, this part of the photobleached brown carbon will become the normal organic carbon for the radiation consideration. And another two new things we need to add is the refractive index for this aerosol species, which goes to the MIYAKE calculations and further goes to the radiative transfer calculations, for example, the RRTMG. And finally, we will connect the Dwarf Chem atmospheric deposition of the aerosol species for the dry deposition and wet deposition to the snowpack processes. Here we are using the community land model embedded in the Dwarf model. So we account for the brown carbon aerosol species interacting with the snow albedo and its evolution within the snowpack. Follow the previous SNICA model, which is the snow albedo scheme within the CRM Dwarf. So to give you a more specific role of how we can deal with all these different key new processes marked as red here. So what I'm showing here is the collection of all the previous measured brown carbon refractive index for the imagery part, which is really related to the absorption of capability of the brown carbon species. For primary, which means directly emitted from anthropogenic and biomass burning emissions or fire emissions. Secondary, which means produced throughout the atmospheric chemistry processes. So as you can see, what we do is that we follow the previous study to use the best fitted line for the wavelength dependent imaginary part for the refractive index for both primary brown carbon and secondary brown carbon here, based on the previous compilations of the other valid observations. And then what we do is that we also compare a number of parameterizations and the previous measurements to come up with a bulk or total organic carbon imaginary refracting index. So we are doing this because if we have the pure brown carbon absorption calculated, and also this total organic carbon absorption calculated from this imaginary refracting index, then we can calculate what is the fraction of the brown carbon inside the total organic carbon to make sure they produce exactly the same total absorption, because the brown carbon is the only species that produce the absorption from the in the total organic carbon. So by doing that, we can calculate how much brown carbon inside the total organic carbon as a function of the soot particle over the total organic carbon. So we are doing this because this total black carbon or soot particle emissions is known by the prescribed emission inventory, and this total organic aerosol or organic carbon emission is also known. So this BC to OA mass ratio is known by the prescribed or existing emission inventory. And then using this relationship or parameterizations here, we can calculate the brown carbon emission mass concentrations. So that's one of our novel way to do this. And for the secondary organic carbon for the secondary brown carbon productions, what we do is that we leverage the existing secondary organic aerosols production scheme within the Dwarf Chem, which here we use the mosaic scheme. And what it does is that it calculates this VOC evolution and then use the KPP chemistry scheme to calculate the how much of this VOC will be formed to were formed to be the secondary organic aerosols and condensed to be the aerosol phase. And then what we do is that we assume only the aromatic secondary organic carbon to be the brown carbon, secondary brown carbon, following previous lab and modeling studies. And here I highlighted 3 of the aromatic VOCs out of the total 5 ones to produce the secondary organic carbon. So what we do is that we account for the SOA produced from these 3 VOCs to be the secondary brown carbon production. And for the photo bleaching process, we follow the previous parameterizations to allow the absorption of the brown carbon species to have a E-folding decay as a function of the model time, integrate time, and also the concentration of the OH, which would oxidize the brown carbon to make this photo bleaching occur. Overall, we also need chemical boundary conditions coming from the global models to drive the WRF Chem regional simulations. So what we do is that we go through all the literatures, and we found that globally speaking, the brown carbon accounts for about 20% of the total organic carbon concentrations. So here, what we do is that we use the global chemical boundary conditions from the CESM model, and then we assume because the CESM model currently accounts for the total organic carbon. So what we do is that we assume 20% of the total organic carbon coming from the CESM model becomes brown carbon as a boundary condition to drive the WRF Chem simulations. So here in the next few slides, I'm quickly showing you some of the preliminary results from our brown carbon implementation of by using the WRF Chem simulation. So here I'm showing the 12-kilometer simulations over the entire Asia by these newly implemented brown carbon schemes in WRF Chem. And here I'm showing the biofuel burning, which essentially represents the brown carbon source from anthropogenic emissions. I will note that based on the current evidence, the brown carbon is not emitted by the fossil fuel burning too much. So here we only account for the biofuel anthropogenic burning. And also here I'm showing the fire emissions for the brown carbon. And if you look at the surface concentration of brown carbon, you see it actually tracks these emissions very well for the pattern. We have a very high emissions and surface concentrations along this southern slope of the Himalaya regions and also northern India, as well as the eastern China area. Here I'm showing you the aerosol absorption optical depths for the brown carbon at different wavelengths as the output from WRF Chem. So here, what we see that the main absorption for the brown carbon actually occurs at near UV wavelengths, which is 300 nanometer, and it decays very fast as we go to higher or longer wavelengths. I should also note that if we look at the downward slow radiation spectrum at the top of the atmosphere, we see that these near UV wavelengths only accounts for very small amount of the total solar spectral energy, which is about 8%. So that's why in the next slide, you will see that the total radiative effect of this brown carbon is actually relatively smaller than the soot particle or dust particle, which actually shows the stronger absorption in the visible wavelengths. Okay, so here I'm showing the total shortwave and long wave radiative effects for the brown carbon for the top of the atmosphere on the left column, the surface on the middle column, and also the atmosphere only on the right column. So if we look at this shortwave first, we see that at the top of the atmosphere, it shows a total cooling effect, which is a negative radiative effect for the brown carbon. And this is contributed by or can be attributed by the very strong cooling effect at the surface, which makes sense that the aerosols blocking downward solar radiations, which generates very strong cooling at the surface. And this is partially compensated by a warming effect in the atmosphere. This is because the brown carbon can absorb the sunlight, solar radiation at the near UV wavelengths strongly. So, but you see that this warming effect is relatively small because the strong absorption mainly occurs at the UV wavelengths, which accounts for only 8% of the total solar spectral energy. And if you look at the long wave radiative effect, then we see almost a negligible top of the atmosphere radiative effect. However, this is attributed to the warming effect at the surface and the slightly cooling effect in the atmosphere. The warming effect at the surface is because this aerosol layer is mainly acting as a cloud to warm the surface, like the low-level cloud to warm the high-level cloud to warm the surface, because it scatters back some of the long-wave radiation. However, I should note that this long-wave radiative effect is 1 order of magnitude lower than the short-wave effect. So the total one will be dominated by the short-wave radiative effect. Finally, if we look at how this brown carbon deposits onto the snow-covered regions, then here I'm showing on the top left, it's the total deposition flux for the brown carbon aerosols, which is generally follows the concentration or emission patterns, where you have a strong brown carbon concentration and emissions, then you will have a stronger total deposition, which makes sense. And if we look at how the concentration of the brown carbon inside the snowpack, which is showing the top right panel here, as we can see, of course, this only happens where we have the snowpack, which is why you see here, we only show this type of a pattern for the general case here, because we don't get much snowpack over other area. And we see that here, once we have the snow and co-located with a very strong brown carbon total deposition, then we will get this very high brown carbon concentration inside the snowpack in the northeast China, and also some of the southern slope of the Himalayas, if you look at it here. And this snow concentration, this brown carbon inside snow will induce snow albedo reduction, which is shown on the bottom left panel. As we can see here, particularly for the southern slope of the Himalaya regions, as I pointed here, you can see a relatively stronger brown carbon induced albedo reduction compared to other regions. And if we look at how this albedo reduction translated to the surface radiative forcing, then we can see here over these areas, it can have this radiative forcing can be more than 0.05 watts per meter square. And I should note that this number may be small for this case study or for demonstration here, because this is January. We don't get much downward solar radiation in at this time. So if we look at this in March or April during the peak snow melting period, then this radiative forcing can be up to like 10 watts per meter square, which is really a very strong forcing drivers for the accelerated snow melting, especially over these Himalaya regions, which causes a lot of concerns in terms of the water resources in the downstream. And this is part of the reason why we want to look at this issue. And with that, I would like to stop here and just to present some of our ongoing work to follow up this implementation. One is to we are currently conducting a comprehensive evaluation of all the relevant properties from our model output, including the aerosol properties like total aerosol optical depth, the absorption absolute depth, the single scattering albedo, and the aerosol concentration in the surface by comparing with the satellite and in situ measurements. And the second one is that we are conducting a production run for 17-year simulations with the data assimilation of the MODIS aerosol optical depth and the MOPIT carbon monoxide to have a reanalysis data set produced for future use. This will be a very useful data set for future studies for the Tibetan Plateau areas. And this is also part of our deliverable for this NASA-sponsored or supported project. And with that, I would like to stop here and take your question. Thank you.
Okay, thank you, Senlin. Are there any questions? I don't see any in the chat yet. While maybe you're formulating questions, I'd like to thank all the speakers to this session. They're excellent talks, and we persevered through technology problems, and we're close to on time. And not seeing any specific questions for Senlin, are there any questions for any of the other speakers in this session here today?
There may be a question for Oli, if Oli is still around, from YouTube. This is for people watching on YouTube. Someone is asking about verification over Brazil. If you have any observation to verify your simulations or forecasts in Brazil.
Yes, we have.
Okay, good. Go on.
Something around 3,500 stations there. I don't have the most recent verification, but I think I could send you at least a couple of preprints from last year's. So maybe just drop me an email. That's would be quicker. I think my email.
Yeah.
Is your email available in your talk?
Yes, and I think it should also be on the. Let me see. On the workshop in the abstract. But it's on oh, sorry, it's on the first slide.
Okay, yeah. Yeah.
Okay, I see everyone has had a long session here, 2 sessions. I want to thank everybody for their patience and for a lot of good talks. And we have one more day of the WRF MPAS workshop tomorrow, starting at 9 Mountain Time here in Colorado. So I think we will end things for the day. Wei or Kelly, do you have any announcements you wish to make before we close?
I don't think so. Just for those speakers of tomorrow, if you have the slides ready, send it to us. And if you want to try it, log in or join the meeting a few minutes early, we can try to bring your slides up. And that's all.
Okay, thank you.
Thank you. Bye-bye.